Ja, ja, wir warten ein bisschen. Ist okay. Yes. Yeah, I thought probably wait a minute because it takes so long before they come over, right?
People started late, of course, with the coffee break. So, people are coming, yes.
Yeah. I think still 1 minute. That's okay. Yeah, still wait 1 minute. Okay. Okay. Should we just start?
Yes, please.
Okay. Okay, I would like to welcome you to the mission session, the Mission 1 session today. We will still wait, probably, or not, we are not waiting now, but potentially people are still coming from the coffee break, but I think it's still good to start already with the first presenter. However, I'd just shortly like to present myself. I'm Irina Heinzig from ETH Zurich and DLR, and I'm very happy to chair this session with Björn Roman here from ESA ESTEC. So the mission is a little bit a mix of different topics. We have topics like the first one, which will look more into detail into the two-look imaging mode for ROSE-L. Then we will have a presentation in combination with NICER and ROSE-L to see if there's an opportunity to fly together. And then we have a 3D deformation monitoring presentation about a new mission called CHORUS, and one completely different topic, which is dealing with a long-track SAR interferometry, which will be presented here also using TandemX data. So it's a little bit a mix, but I'm very happy to listen to all these different contributions, and I'd like to present now the first author or the first presenter, which is Simon, Trumpf, so I'm from DLR, and he's talking about the exploitation of two-look ScanSAR with ROSE-L for along track surface deformation measurement.
Yeah, thank you for the introduction. The topic is one that already popped up 2 days ago when talking about ROSE-L in the first place. We did some simulations on the accuracy of deformation measurements with ROSE-L. And I'm not going to go any further, I'm just jumping right in there. First, the motivation. Why do we want to measure the long track deformation? Most of you will be familiar with the problem. We have the issue that most satellites are in a quasi-polar orbit with the side-looking geometry, so we have a very low sensitivity towards north-south deformations in current SAR missions. And we need the north-south deformation, or we need the sensitivity for north-south deformations when we want to retrieve the three-dimensional deformation. Now, why ROSE-L in this context? First of all, as an upcoming SAR mission, it's interesting to look into that, but we have some things that would make two-look ScanSAR mode actually possible, which is, first of all, large available bandwidth, and then also the application of ScanSAR. Let me explain quickly what I mean with a large available bandwidth. You can see the antenna pattern. It's the two-way antenna pattern of ROSE-L in the plot, and you can see those very small gray bars which are actually the limit of the available bandwidth. You can see we have quite a lot of bandwidth, but for processing itself, we only use this very small part. Now, our approach would use a larger part of that in order to obtain some spectral diversity with which we could retrieve the along track motion. The approach that we use is 2-lux GANSAR. It's not entirely new, but let me anyway explain a bit what are what we have to consider. First, some words about ROSE-L. Again, most of you will be familiar with it. Part of the Copernicus program, we have as the Copernicus Sentinel expansion missions. We have an L-band SAR sensor. We have a large antenna with 11 meters in length and 5 channels. This is important for the simulations later. We have a spatial resolution in the dual-pole configuration for 10 times 5 meters, and hopefully it's going to be launched by the end of the decade. But now to 2-lux GANSAR. First of all, let's have a look at single-lux GANSAR. Most of you will have heard of it. This is a time-frequency diagram. I think those GANSAR modes are quite easy to explain with the time-frequency diagrams, so I'm going to show some of these. This is a single-lux GANSAR mode. You see we have 3 bursts that we're looking at. Usually they'll have a small overlap. I didn't consider this here in the plot, but you get the idea. And every target, for example, this one, is covered with a certain bandwidth and a certain Doppler centroid. Now, the important thing about GANSAR is when we're looking at the single-lux, the focusing bandwidth, this is not the actual bandwidth that we need in order to compute the azimuth resolution. But what is important for the azimuth resolution is a bandwidth of 1 target. This is what you see in yellow in this plot. Now, for past 2-lux GANSAR modes, we had this configuration, which means that we're basically changing the GANSAR timeline, which leads to 2 different looks of each of the targets. Again, you can see those in yellow. And what you can also see is that both of these looks have actually a smaller bandwidth. This means that the overall azimuth resolution is smaller. We have a certain separation of delta F as well between the looks. But this is not what we're doing here. We're using another approach based on the large available bandwidth that I showed you before. And this is what we are going to do. So we're looking at this 2-lux GANSAR configuration where we're extending the bursts while maintaining the same target bandwidth, as you can see in the plot, just because the bandwidth allows us to do so. This means we have the same azimuth resolution, but if you look at the antenna pattern, again, you can see that in the extended, where's the pointer? Anyway, you can see that in the enhanced areas of the bandwidth, the gain of the antenna pattern actually decreases, so we have to expect some lower performances than the nominal performance in these extended areas. So this is why we want to look at the actual performance when it comes to 2-lux deformation, when it comes to deformation measurements. Like this, with the 2-lux, we can then apply some algorithms which are either found as spectral diversity or MI in literature, also nothing completely new. But this is what the 2-lux GANSAR modes now allows us to do. So the important part to take away here is by enhancing the bandwidth, we're not actually changing the azimuth resolution, but we're changing the coverage of the bursts. And we can lead to the case that we always have 2 bursts overlapping, leading to 2-lux for each of the different targets. Now, in order to compute the accuracy that we can get with a deformation measurement like this, we can take some analytic equations. This is what we're doing here also. This is taken from literature, so this is not entirely new. And we compare it to the single-lux GANSAR case, which would mean that in order to measure the along track deformation, we would apply some cross-correlation. Now we have to be careful because both of these equations depend on the coherence, but there's different cases. Now for the single-lux GANSAR case, it's quite straightforward because we only have 1 look, which we can compute the coherence for. But for the 2-lux GANSAR cases, we actually have those 2 looks, so we somehow have to compute a weighted coherence between the 2 different looks. This is quite straightforward just by taking into consideration the coherences of both of the looks. And in order to compute the coherence in the first place, we consider a temporal decorrelation. We also consider decorrelation due to the SNR, due to noise, and also one due to azimuth ambiguities. Now let's have a look at the azimuth ambiguities first. This is a plot of the azimuth ambiguities over the azimuth frequency. The dotted or the dashed lines are the ones where we have we would have overlapping looks. So one look could be in the center of the burst, and the other look would be then at the edge of the burst. I will not go into detail on how I computed these curves. This is very technical, but feel free to approach me if you want to know. I have some plots on that. And then we can also have a look at the SNR in order to compute the coherences. For this, we take the gain, we take this equation that is in the top right of the plot, where we take normalized reflectivity factor, beta naught, we multiply it by the gain, and we divide it by the noise power that we have. And overall, if we take all of this together, if we compute the coherences from there, then we get to this. Anyway. We get these two curves over beta naught. And you can see that the two-look Scansor approach is way better than the single-look Scansor, the cross correlation, the reference. It's about a factor of 5 to 6, depending on where you look. And this means that the two-look Scansor approach is actually very well suited in order to, or much better suited in order to compute the along track, in order to measure the along track deformation compared to the single look case. If you look at the parameters, maybe it's worth mentioning as well here that we're using a number of looks of 70, so we have a resolution, a spatial resolution of 50 times 70 meters, and we were assuming a temporal coherence of 0.7. Now, this is only part of the whole truth because we're just assuming also azimuth ambiguities as noise here. And we want to know how exactly that would look like, and we want to simulate a bit more. We have the capability of doing end-to-end simulations. We did that, and I'm going to present how we did that and the results now. First of all, the input data. We want to make the input data look as realistically as possible. So we take an actual reflectivity image from Sentinel-1. This is the reflectivity over a scene over the Turkish-Syrian border region, so close to the East Anatolian Fault. The scene size is 150 kilometers times 45 kilometers. You can see the spatial resolution there as well. What we actually do is we upsample that image to 15 times the PRF that we would have in rows L in order to be able to introduce ambiguities later. And then also we need an interferometric phase. And for this, we use a deformation that we have generated using the Okada model in 3 dimensions. This is with a finite rectangular source, imitates a strike-slip fault deformation. And while generating this deformation, it was particularly important to have a strong northing component because this is the part that we want to measure in the end. So this is how the deformations look like, not too spectacular. And then we use this for the simulation. Now the simulation consists of 4 different blocks. First of all, we have the scene generation and the radar module, which together generate a raw SAR signal for the 5 different channels of rows L. And then we have a simplified retrieval chain as well as the evaluation in the end. The evaluation takes the true deformation that we have at the input and compares it to the retrieved deformation that we got from the retrieval, and then computes an error, and we can analyze how accurately we actually retrieve this deformation. So I showed the amplitude. Of course, we do 2 different acquisitions because we want to perform interferometry. You can see the interferometric phase from the input here, and then we come to the radar module. Now in detail, what the radar module is doing is basically taking the upsampled image, it's a complex image at that point, and defocusing it. Then we are we're filtering it with a multistatic filter. This means we're actually considering the different channels. We have different channel impulse responses depending on the channel. So after that, we have 5 signals for each of the channels. We perform some subsampling in order to introduce ambiguities. Then we introduce system noise. Of course, this is uncorrelated between the channels because it's different for each of the channels. And in the end, we're considering the Scansor timeline. So we're basically cutting bursts from the raw data. Then the retrieval performs the azimuth reconstruction. So in order to get one signal from the 5 different channels, this is needed. It's some kind of beamforming on receive. And we're performing some burst-wise focusing in order to be able to compute the differential interferograms between the looks in the end. And then we have the interferometric chain that is depicted below. It consists of a two-look processing chain and of the single-look processing chain. And I'm going to explain that more into detail in the following slides, and I'm going to present the results of each of these parts. So first of all, let's have a look at the two-look processing chain. What you can see here is first the differential interferometric phase between two looks for the entire image, and from there derived a long track deformation. And of course, we can use both of those and compare them to the input, and what we get as error is this. So you can see, and you see it a bit better in the phase error than in the actual deformation error, that we have some different variances in the error. So I would assume it's zero mean, but it depends on where you are in the burst on how much the variance actually is varying. Now, if we take the retrieval error, there you can see these variances not that much, but we can still compute the variance for each of the azimuth lines, and what we get is that. And if we then also plot our analytic results that we obtained from before, how I explained that, for a worst case and a best case, depending on where in the burst we are, then this is what we get. And you can see the analytic results and the simulated results actually match quite well. So yeah, seems good. We can then analyze what we're actually seeing. And if we look at the initial acquisition, this is what we get. So you can see that actually at the burst centers, the variance is the highest. So the retrieval accuracy is the worst. At first, it's a bit unintuitive, but it becomes clear when we're looking at the antenna diagram again at the gain, where you can see that actually because of the two looks for each of the at each burst center, we not only have the good signal from the burst center, but we also have the worst signal from the burst edge, and this is why the accuracy is actually worse. The worst at the burst centers and the best in between. Now we can play around with the simulator because we have it. We can change a lot of parameters. We changed different things. We changed the ambiguities that we inserted, so we can simulate all of this without ambiguities. We could change the noise, for example, but what is important, or what is interesting to see here now, is an approach where we change the antenna pattern, actually. There has been a publication at IGARS where it was proposed to change the antenna pattern of Roselle, to change the transmit antenna pattern by changing the phase spoiling to be wider, as you can see here. But like this, of course, we lose some gain. And we performed the same simulation with this antenna pattern, and you can see the overall performance becomes more smooth, less dependent on azimuth, less dependent on the position in the burst. And especially for the bad part, it gets better, but also for the good parts in the simulation, it gets a bit worse. Overall, it stays in the same area of accuracy. Can we go back? Yeah. Stays in the same area of accuracy. Now, this was the two-look processing chain. This is the results that we got from there, and now we can even apply the retrieved deformation on the single-look processing chain. So this is just a standard interferogram from the single-look acquisitions. And what you can see, let me try again with the laser pointer. What you can see is actually jumps in the interferogram due to the different bursts. So for example, we have one here, we have one in the middle here, and you can clearly see them in the error to the zero Doppler phase, which is depicted on the right. And on the right, as you can see, this is the difference between the zero Doppler and the line of sight interferogram that we have. So this is basically the along track, the attribution, the contribution of the phase, of the along track shift to the phase in the line of sight. And now when we take the secondary acquisition of the single-log interferogram and we reinterpolate it with the retrieved deformation in an along track, we can actually remove those shifts. So what we did now is we basically, with this processing chain, retrieved the along track deformation separate from the deformation in line of sight. And you can see the error of the phase between input and what we simulated is around 0, except for some areas with high decorrelation, for example, this lake in the bottom right. So to conclude my talk, we have shown that it's actually possible to take ROSE-L, to apply two-look scansor on it, and to measure the along track deformation with that in an order of the accuracy is in an order of magnitude between 8 to 9 centimeters, while having a spatial resolution of 50 times 70 meters. However, this still depends on the multi-looking. So if we increase the number of looks, then we will get even better than the 8 to 9 centimeters, but of course with a coarser resolution in space. As well, we can use this along track deformation to correct the single look interferograms. And we could also use this technique, for example, in order to correct, that might be an experiment to use this in order to correct for jumps at ionospheric height as well. That's just to try out. Yeah, that concludes my talk. Thank you for your attention. And I'm ready to take questions.
Okay, yeah, thank you very much. So we can allow some questions.
That was a very interesting presentation. Thank you. I just have a question. So with your azimuth reconstruction using the apertures, I know so you're using basically you're scanning a beam using those apertures instead of using kind of a displaced phase center approach. Is that true?
Not entirely sure if I got the question correctly, but what we're doing with the azimuth reconstruction, it's an algorithm which is not steering in time, but it's reconstructing actually different intervals of the Doppler spectrum. And like that, in the end, we get the full spectrum at the same time. It's just weighting, a kind of beamforming on receive with weighting of the different channels in order to get the different parts of the spectrum.
So my follow-on, I'm just wondering, is there any performance dependency on the pulse repetition frequency? So would you have, is there like an ideal frequency where your performance for the displacement estimates would be better? I'm just wondering if there's a dependency on your choice of PRF.
Yeah, there's a very high dependency on the PRF. So when you change the PRF, a lot of different parameters change at the same time. So for example, the azimuth ambiguities change rapidly. And also, of course, the reconstructed spectrum, mostly the ambiguities gets completely shifted. There's completely different values there. So it really depends on the PRF. That was one of PRF that we assumed, which is, to my knowledge, it's a preview for ROSE-L for the first subswath. So we tried to stick to what is now in ROSE-L. So that will be fixed, or will it be dependent on the orbit height, the PRF? Of that, I'm not sure. I'm not too much in the construction process of ROSE-L.
One more question there, yes. Malcolm.
Thank you very much for the presentation, and I really enjoy seeing how you try to take the system as it is and see what you can sort of propose further. Just a question, which is, these types of schemes never come for free, as you can imagine. It would be too nice to be true. And clearly, it's one that brings a little bit of angular diversity in the actual acquisition, so that gives you your better azimuthal performance. But at least for the other proposed method, you pay a price in terms of the noise equivalent sigma 0, and you drop by not just 0.5 dB or even 1 dB, but 3 to 4 dB. Does your scheme more or less have the same trade-off? And then taking into account the noise equivalent sigma 0, I think you used a C-band reflectivity map and not an L-band, which is can be quite different.
Yeah, I mean, the reflectivity was from Sentinel-1, so it's C-band. But in the end, I'll have to think about this a bit more, but I think that in the end, it's just the amplitude that we took. So we have an incoherent image. The amplitudes are different, and in the end, what the scene is, not sure. Maybe we can talk afterwards if you have some inputs about how the reflectivity changes between C and L band, because I haven't thought of that, to be honest. But yeah, we took the noise equivalent sigma 0 trade-off that you mentioned. We took that into account. So the other antenna pattern, which is broader, actually had this around 3 dB difference in the main lobe of the antenna. And this is also why we got the results, how you saw them here. Otherwise, I think they might have been a bit better.
Yeah, okay.
Okay, thank you. So, thank you very much again.
Thank you.
Okay, our next speaker is Marco Lavalle, who will present co-flyers, mission concepts for NISA and Roselle, trying to explore further, let's say, bistatic concepts that are to come. So hopefully they're going to stay also beyond harmony.
That's right.
Marco,
Yeah.
the floor is yours.
Thank you, Bjorn. So yes, as Bjorn anticipated, I will be talking about some of the activities that we're doing at JPL, but also in collaboration with ESA, and you see some of the names of people who are actually in the room today to explore concepts for co-flyers or companion missions, specifically for L-band missions like NISAR or Roselle. We started with NISAR, so we're more familiar with the NISAR parameters, and in fact, I think I presented some of the plots that you'll see today for NISAR at IGERS, but I updated them with the Roselle geometries, and so some of them are updated compared to what I presented at IGERS, as well as some additional analysis. So the background for this is what we call SDC, Surface Deformation and Change in the NASA nomenclature. So the Decadal Survey in 2017 recommended surface deformation and change as a designated observable, and so as a result of that, NASA and the science community created a science and application traceability matrix, or SATM, where we list a number of scientific goals. And with scientific goals, we also have an idea of accuracy and performances that we would like to see in terms of deformation products. So one of them that I'd like to draw your attention is the sensitivity to high change is between 1 to 10 millimeters, so it's fairly accurate, and so that calls naturally for atmospheric correction. There is also a goal in that matrix that is associated with the 3D deformation vector, and that's actually what I refer to in the title with emerging needs. So we're focusing in this presentation on the ability to retrieve the 3D deformation vector, as well as the compensation for tropospheric range delays. So in terms of more at high level, SDC started with a big study. We looked at different architectures. Then these architectures were down selected to 12 last year, and they were further reduced to 5. And so we're currently studying only 5 architectures. And I will be talking about only one of these architectures that we just started to study. That's called the Roselle architectures, and involves essentially co-flyers. So we started to study now this architecture, and we'll be studying it for the next 2 years in collaboration with ESA. Another thing that I can point out in the last bullet point is that we're cost capped, and so partnerships are encouraged in this particular study. So this is a plot that shows the timeline of SDC compared to NISAR and other missions that are in the pipeline for especially at ESA. This shows essentially that SDC is something that will continue after NISAR phase in beyond 2030, and of course our aim is to align it with the launch of Roselle. In terms of emerging needs, we also have what we call the NASA STV, Surface Topography and Vegetation. We don't see that much in this workshop, where probably the community is more versed to deformation, and so zero baseline interferometry, zero cross-track baseline interferometry. For STV here, was also recommended by the Decadal Survey to observe the vegetation structure and the topography, so the barrier topography. And so NASA is also studying this concept. So we also have a science and application traceability matrix. The community is different. It's typically, perhaps the community in Europe, it's the one that attends the Polinzer workshop. And so what we're trying to do is we're trying to also jointly studying the concept for SDC, the surface deformation, and STV, so the surface topography, which will benefit many of the application, of course, in solid Earth as well. So I don't have to go over the benefits of the co-flyers. They are affordable, flexible, and scalable. But I wanted to point out here that the way we're approaching the study is by looking at 3 components. First, with very simplified equations. We have seen some of them in one of the talks for harmony, for example. And that's what I'll show today. We're also building an end-to-end scattering simulator, more related to what the previous speaker talked about. And we're also looking at multi-static SAR campaigns in collaboration with some of the European partners. The trade space that we're looking at for this study is quite broad. Today I'll also only show a few variables. So in general, we know that SDC essentially and the retrieval 3D deformation vector is calls for the multi-screen TINSAR, and so we're looking at along-track co-flyers. For STV instead, we're looking at tomography or pull-insert technique, which is essentially implemented with the cross-track co-flyers. So we have competing system requirements, if you like. But I'll put some emphasis also on the multi-static mode. So for co-flyers, passive co-flyers are typically more suitable for Roselle or NISAR, just because we're not cooperating with the system. The system is what it is, but we're also exploring other multi-static modes, the CISO or the SIMO, where we have the co-flyers in an active transmission and reception. So right, the SIMO is when you just collect, you have receive-only co-flyers. You collect the signal that is transmitted or is bounced off the surface by Roselle or NISAR, whereas the other two modes are more complex and also more expensive. In terms of the instruments, I started, like I said, the Roselle is, all the plots that you'll see are using the Roselle parameters, the 240 or 250 kilometer swath with the Sentinel-1 orbit. We're not dealing yet with the mode of Roselle, the HRWS, right? The combination of the scan and receive and the maps. But this is something that it's definitely on our to-do list, probably top priority to understand to what extent we can have co-flyers with that mode. In the receiving side of the study, we're keeping the number of receivers very small, 2 to 4, to keep it affordable, and also because there are other parallel engineering studies that suggest that it's easier to have in a single launch 2, 4, or few co-flyers, especially if you look at the ESPA or ESPA Grande type of spacecraft. We're not considering SWIPSAR or SCORE in reception, like I said. So this is the first concept. I'll show two quick concepts that just to brainstorm. The first concept is 4 along-track co-flyers, 2 for each Roselle spacecraft. They are essentially for each spacecraft. We have 2 co-flyers, 1 leading and 1 trailing Roselle at the space at 250 kilometers, and I have a plot after this slide showing why 250 kilometers. The swath width is relatively short, narrow compared to the Roselle swath because we have other constraints on the antenna sides. We're using an antenna sides here, 12 by 2 meters for the co-flyers, which folded can fit into an ESPA Grande satellites. So there's other constraints, and of course there's some other calculation done for ambiguity and noise equivalency mod 0 just for the receive only to come up with that swath width. But just in a nutshell, the pros of this architecture is that we can get the 3D deformation vector with 6-day interferograms, but we're only illuminating 1/3 of the Roselle swath, and we cannot do surface topography and vegetation easily unless you reorganize the satellites a little bit like Harmony is doing. So this shows essentially the solution of the multi-squint repeat pass SINSAR equations. Nothing new, it's fairly standard, it's geometric model, and so you solve for the model, and then you get the accuracy of the 3 components, and you can essentially see why we like bistatic angles between 10 and 20 degrees, just because they give us a fairly good accuracy, especially in the SIMO mode. So what we did essentially to come up with the 15 degrees, we started with the SIMO mode, so the orange curve, we have receive-only satellites, and we took 5 millimeter accuracy as an average accuracy informed by the science and application traceability metrics, and we essentially come up with the 15 degrees bistatic angle, which in the Roselle geometry correspond to 250 kilometers along track baselines. Just as a note here, if you have SISO or MIMO modes, so more complex receivers or multi-squint systems in general, you get a better accuracy. So you can either go with the smaller bistatic angle, which do have some advantages with geometry and overlap of the beams, which I'm not dealing here. And so that gives you a better performance essentially. The disadvantage of this architecture or this option A, is, as I mentioned, the fact that we cannot do STV, and if you sort of flip the problem and you try to see what is the maximum along track baseline that you can tolerate to do interferometry, single pass interferometry, right? So with the monostatic Roselle image and the bistatic Roselle co-flyer SLC, you see that the bistatic angle is very narrow. It's much smaller than what you need for SDC. And so this is something that essentially it poses a limit on the along track baseline that you can have. You can also look at the multistatic modes. Kind of the good news is that the SIMO mode is not really the most strict mode. So in the SIMO mode, you can tolerate twice of the synthetic aperture length, which with Roselle is about 17 or 18 kilometers. So that's what comes out of the study. Now I have to give a note of caution that we may be able to tolerate longer along track baselines if we use a different technique, and I'll get to that for the tomography, and I'll get to that at the end of this presentation. There is one option that we can, one thing that we could do, we could drift the orbits, so to get the cross-track baselines and do STV. So it's essentially the same scenario. Option A, you have a trailing and a leading co-flyers, and then at every pass you start drifting the orbits, right? And so you build a tomographic stack, so you can do some tomography with that. It's a repeat pass tomography. It's not really good for tomography, so we would like to have it single pass, but it's something. And so the question here is, what is the impact to the SDC performance? If you put a height of ambiguity of 50 meters for the tomography, you see that in the orange curve, you need about 12.6 kilometers of drift, which impacts only by 10% the number of looks. It's only 10% look reduction in the deformation to get the same performance. So it's not too bad. So if you have a time series in the deformation that's where the orbits start drifting, you can compensate for the poorer performance by just increasing the number of looks. So this is just to say that it's not a huge deal. I think it's not completely breaking the time series, as sometimes we feel, right, when we like varied zero baseline for deformation. The other option that we have is the cross-track co-flyers. The advantage, so here we're not having a leading and trailing satellites. We put all the sort of a cluster of 3 satellites in one side of Roselle, and to keep the number of co-flyers small, we're limiting to 3 co-flyers. Of course, you can have 6 or 9 or 12 by adding more co-flyers to either side of the Roselle. So in this option, we are illuminating at the same time one sub-SWAT at the time, and so we're covering in one pass the full Roselle SWAT. The disadvantage here is that we are only observing one component, either the 3D deformation vector or the atmospheric correction. So that's, we're essentially giving up one of the components. And also to switch from the SDC to the STV phases, we need some repointing, right? Because SDC needs multi-squinting repeat pass, whereas STV needs a single pass cross baseline. So that's where the issue is. So jointly do these two measurements. It's not straightforward. In fact, I think Harmony is doing different phases from what we have seen on Tuesday. So here, what I show is essentially a plot where I ignored one of the multi-squint observations. So I solved this system with the cluster of co-flyers, the 3 co-flyers, and essentially ignored the 3D deformation vector and just focusing on the atmosphere. And you can see that the performance just reduced by a little bit. It's not too bad. So in fact, you can compare the middle plot with the right plot. So that was the option A. You see the vertical axis, you go from 14 millimeters, and so the range to 12 millimeters when you go from option B to option A. So it's not too bad in terms of reduction of performance when we are just using one set of multi-squint observation instead of the leading and trailing option. And if you do the same exercise by ignoring the atmosphere and just focusing on the 3D deformation vector, you get actually even better performance. So that's That's another message. Now, in the last few minutes, I wanted to reiterate something about tomography that is not always well advertised, I guess. So if you look at the tomographic equation, so here we're doing STV, surface topography and vegetation, so cross-track interferometry, and you use the classical equation of tomography, you get that the system that you need to satisfy the STV needs is fairly ambitious. So this plot is, it's essentially two plots back to back. On the left, you have the vertical resolution, and on the right, the maximum tree height, so the ambiguity. So the way I use this plot, I start from the vertical resolution. The STV community wants 2 meters vertical. You draw the vertical line. You select the multistatic mode, say that we select SIMO, and then you draw an horizontal line to go across the other plot to select the number of acquisition that you need based on the maximum tree height. So if you do this little game, 2 meters of vertical resolution with maximum tree height of 50 meters, you get that essentially you need a very long tomographic aperture and about 25 acquisitions, which you can have it either a single pass or repeat pass. So you could essentially think of shifting the cluster of 3 satellites several times to get several acquisition, tomographic acquisition, which is a mix of repeat pass, a single pass, cross-track interferometry. So this doesn't sound very practical. And so we're thinking in the study to applying this technique we call histogram tomography. This histogram tomography is actually a very simple concept. The idea is to build the tomographic profile by looking at the interferometric phase at full resolution. And instead of building the histogram by accumulating the interferometric pixels, so the number of pixels, we're essentially accumulating the backscatter for that particular interferometric phase. And so you build essentially a backscatter INSAR profile histogram that looks like a vertical profile of vegetation. So we validated this with some data during the AFRISAR campaign. This is an airborne experiment that I showed earlier in previous conferences. And so that actually gave us good results when we tried to extract the digital surface model and digital terrain model from which we extract the canopy height using single baseline, by the way, and a single polarization. So we're using this technique now to inform the mission design, and we're just moving the first steps to develop an error model for this technique. And this is just one of the charts that shows how to link with a very simple model the vertical accuracy to the signal to clutter ratio and the height of ambiguity. I guess the message of this technique is that you can assume that there is a dominant target in the canopy, so that's why at full resolution you can always get some scatter within the canopy, and if that scatter is sufficiently stronger compared to the clutter around it, so you can reconstruct the vertical profile. I don't know how I'm doing with time, but I'll wrap up. So I show essentially the beginning of a study that we're doing to hopefully address emerging measurement needs with co-flyers for Roselle. So the ideas are perhaps similar to what Harmony is trying to do with Sentinel-1. We have various options on the table that are being studied, and we're exploring the trade space in different ways with simple equations and also, like I showed today, but also with complex simulations. The ambition here is also not only to look at the 3D deformation vector and atmospheric correction, but also at keeping an eye on what we can do for 3D vegetation structure retrieval, which ultimately, by the way, benefits solid earth and other scientific disciplines that typically come to these fringe workshops. And that's all I have. Thank you.
Thank you, Marco. Thank you for this very nice presentation. I think you gave a nice overview of where you are currently. I guess there are some questions. If not, then oh, there's one question. Yes, Otmar.
Thank you. It's more a technical thing. So in the plot where you showed the based on the baseline, for the baselines based on the height of ambiguity of 50 meters. So did you assume specific instance angles, since Roselle has a very wide? This is changing quite a bit depending where you're on the swath.
Yeah, you're absolutely right. So that's just in the center of the swath, and so yes, those performance
quite dramatic change, I think, to be expected for the other.
So yes.
Angles. Yeah. Okay,
yeah.
Thanks.
It is, yeah, incidence angle is important for all the plots that have been shown. I think there's a 10-degree excursion or even more of the incidence angle.
More question? Marco, I would have a question. I like very much the thing what you tried, especially in option B, where you're using, let's say, try to extend the swath with multiple flyers. I think this is something that, of course, allows, let's say, things to have a relatively simple spacecraft design and increases the let's say, reconfigurability of the overall system in the end. But I noticed that of course, you take into account quite some constraints already because of the program you're in right now. Is there any attempts to have more, let's say, open, let's say, interferometric cartwheel studies to be done on the JPL side in the future that is less, let's say, constrained by, let's say, the mission context that's currently out there?
Yes, so we are, so for STV, there is a study currently done to also revisit the science recommendation or science requirements to see whether the observing system that we come up with, which by the way include also LiDAR, is viable. And so, yes, there is a study that looks at the full program of record, other satellites, and as well as what can be achieved realistically. So 2 meters was actually coming from a previous study that was done. And so now we're basically looking at whether we can achieve that, and maybe other missions, a LiDAR mission, for example, will achieve that. And so in some areas, and so we're planning, we're architecting this mission based on all these aspects. And so we will also look at what ESA is doing with BIOMAS mission, for example. Although I think the resolution is a little coarser for BIOMAS. So.
Yeah. Okay, thank you.
Thanks.
Okay, then we're going to the next speaker. So the title changed a little bit. This is Dominik Richter from the German Aerospace Center, and his new title is On the Removal of Coherent Ambiguity in SAR Interferograms, a study for harmony, sorry. So it's, I was mistaken saying later on it is a long track mission proposal.
It's fine.
Or study.
Thanks for the introduction. Welcome everyone to my talk. This talk is, I changed the title to fit it a little bit more into the scope of this workshop here. But if you think about coherent ambiguities in SAR, you think maybe why coherent ambiguities? And I'm going to tackle all these questions today. So what coherent ambiguities are, how the impact is on interferograms, and this is all done in the scope of the harmony, the long track interferometric phase, the stereo phase where we do the measurements over oceans. But I don't want to lose your attention here, because the long track interferometric mode is actually quite similar to differential interferometry. So when we have azimuth ambiguities here, you see Sentinel, for example, flying over a scene where we have this black target here, some kind of feature, earthquake or whatever. Then it's imaged, and because the SAR is a Doppler system which continuously measures the Doppler, then we also get ambiguities in the sampling of this Doppler, which is shown here in these red lines. This means, when we're looking zero Doppler, then there will be at some points at multiples of the PRF some kind of signal, which is here this black target, and is imaged then into the zero Doppler geometry as this light blue target. Could be different, but the important thing is now when we add a second track, a second acquisition, and this has a small baseline towards the first acquisition. You saw there's now appearing a blue target, or a blue feature, blue ghost of the black target, which has changed maybe by a few millimeters, and this blue target overlaps with the light blue target. And this indicates here that whenever we have ambiguities and we do interferometry on small baselines, for example ATI or differential interferometry, then those ambiguities can become coherent. What does coherency means here is that, yeah, in basic it behaves like the main signal. You see, for example, on the right here, there is this main signal blue M, which is the signal of interest that we're wanted to measure. It's the underlying here within this green spot. And then we add here somewhere those vectors from the coherent ambiguities, and the phase is not necessarily the same, so they introduce a bias because we add them coherently, and then we're resulting somewhere in this green vector, which means there will be a phase bias indicated by this opening of the two vectors. Of course, there are more ambiguities. There's not only one, but the example here is only for one. Now, for harmony, this means the ATI phase. I give just a figure. Is here a C-band system with 10 meters baseline. Then at about the ambiguous to signal energy, which we receive for harmony. The thing here is with harmony, we have a receive pattern that is way broader than the sentinel. So sentinel shouldn't have a problem, but with harmony, we expect around -12, -13, or -11 dBs of ambiguous to signal energy. And whenever this delta phase between the signal of interest and the coherent ambiguity is, let's say, 20 degrees, then we get about 1 degree of phase bias. And this phase bias then translates, for the case of harmony again, here into, let me show over there, into somewhere 12 centimeters per second, which is almost using all the margin of errors we can accept for the harmony mission. It's easy now to suppress those ambiguities, especially in the interferogram, because we saw there's like a shift in between the signal of interest and the ambiguity, so the signal where the ambiguity originates from. And if we can then just apply those shifts to the interferogram, it's this scheme over there, then and multiply with some values, add the interferograms add them up, then those phase bias could be somehow corrected. I'm using now here a scene acquired with TandemX, and you see here, for example, if you draw attention to the red circled areas, there is some coherence loss due to the phase biases. So you see some fringe patterns here that occur due to ambiguities. And looking into the interferometric phase, there's also the phase bias visible, especially here in this area. Now we are applying the scheme, shifting the interferogram and weighting, summing up. Then these phase biases can be corrected. Now, when we go into harmony, we're not acquiring data over solid surface, but over ocean. And what we see here is sublooks of sliding spotlight data over some area over the ocean. And it's quite hard to see, but there is some shift in the phase that we're measuring. So these sublooks cover then also the ambiguous area. And during the acquisition, so this means the phase is not stationary. If we do some more quantitative analysis, you see on the right this TandemX spotlight data plot is produced from the interferograms, from the sublooks, and we're plotting here the phase L1 from the first look, and plotting then all the phases from these subsequent looks, plotting those over the phase L1 from the first look. Then you see there's a change. These phases do not necessarily correlate. They are changing over time. So from L1 to L2, L3, L4, this scan over time, and you see that these phases do not correlate. It's quite hard to see and also think of it because the acquisition here has a height of ambiguity, so this is not zero or not infinity, so there's no non-zero cross-check baseline. So I did also some simulation with a purely monochromatic wave, and there you can see as well that there's a change in the phase. What does it mean? So if we apply this technique, Paco proposed here the infinite impulse response equalizer. It's just an advanced shift technique. Then this technique requires stable signatures beyond the synthetic aperture time. But we've seen for oceans this is not working all the time, not necessarily working. I'm going to have a little bit of look into this. And we proposed then also a different technique that is working on an ambiguity diversity scheme. So if we produce from the synthetic aperture multiple looks, and then we can see that we can modulate these ambiguous signatures. And you see here in the top right, there's 4 looks for a scene over Russia. You've seen this scene before. This is just a cutout, and there is now changing biases. There's even in the top left of L1, there's like something appearing that is outside of the interferogram. And when we then go through all those looks, you see this changing, and we're going to leverage on these ambiguity diversity and proposing here a scheme to correct for those. And by staying within the synthetic aperture, we can encompass that the signatures change over time. And the scheme then itself is quite simple. We have the 2 SAR data, produce them into SLCs, then do some look processing, form the looks, form an interferometric stack of looks, and then apply, like, just summing up those interferograms with looks, with weights that are generated according to minimize the mean squared error. You can see on the right the equations here. And there's here this matrix T is just the weights, some constant factor M, and we can apply different techniques here. Not really going into details. Maybe here worth noting that the semi-adaptive here is estimating all the covariance matrix which we need to form this matrix T. And this semi-adaptive means it can adapt to all the signatures of the interferometric phases that we're seeing in the interferogram. Then we did some Monte Carlo performance analysis to check how the algorithm works. And we see here that for the asymptotic analysis, that when we increase the numbers of samples, that here the bias is removed. The green one would be with biases, and here the blue ones, the biases can be removed. And you also see that there's a little bit of bias variance trade-off, which we can accept, because when we now look into the more detailed analysis of the performance in more realistically scenes, you have here quite strong ambiguity to signal ratios of -6 dB, so the summing up the left and right ambiguity. In some modulation of the coherence and some phase bias we get for the scene, and then the resulting phase with ambiguities here. And when we now look into the errors we get with different algorithms, then once we look here at the at the median phase estimate or phase error over the true phase bias, and we see that the interferogram here shows the biases, the bias levels, and with the techniques applied, we can remove those biases. I'm not going into details which line is which, it's just to show that all the algorithms work here. And over the root mean squared error, which combines both the bias and the standard deviation, we see then that we also have some kind of asymptotic behavior. The dotted line is the only standard deviation which we get when there is no phase bias. We have plotted here in pink. Here is the uncorrected interferogram. Then we apply those techniques, and we can achieve here this lower bound for the algorithms. Now, I'm going to validate also this with data taken from real acquisitions. How do we get then ambiguities here? Because usually acquisitions nowadays have a rather good suppression of the ambiguities. So I'm introducing some synthetic ambiguities, which means I'm taking the SLCs, defocus, and split the spectrum. Then in a part with ambiguity, with the left and the right ambiguity, a main part which is then later used as a reference, adding the synthetic pattern to this in the spectrum, then downsampling and refocusing the images, the SLCs. Then we have synthetic SLCs with some higher or less dampened ambiguities, and then apply the removal schemes. What we can see here then, I'm jumping now to a scene that's acquired over the Amazonas. Yeah, you can see here there's some clear cuts in the Amazonas. This should be very high coherence, but because of the ambiguities, there is loss of this coherence. And you can also see a modulation of the coherence here. And also in the phase error, there is then here the like bright blue and red patches are the phase biases introduced by the coherent ambiguities. Now applying those algorithms again, we see here a little bit of this trade-off of the MMSE, because the ambiguity levels are quite strong. And yeah, there's also some effect of the reference noise, because the reference is generated from the same data set. Yeah, you can see, for example, here that the algorithms are worse performing than the real interferogram, which is due to that there's reference noise in the reference. But in the areas with high coherence, we can suppress ambiguities. You can see in the 2D images of the phase errors that there is for these in the 10 kilometers in azimuth, there is a suppression, the IRE, so this infinite impulse response equalizer, and the technique with adaptive ambiguity diversity can remove the ambiguities. And yeah, both algorithms, especially the IIRE, require a lot of tuning to achieve then even better results, because you see there's a lot of margin in the coherence, in this plot over coherence, because we don't achieve here the lower bound. Yeah, now this is the more exciting part for harmony, then also validation on C with synthetic ambiguities. We do again a jump. Now this time we're jumping to a coastline in front of Scotland, some islands here. And you can see around these islands, there's a lot of current flowing, current of the sea flowing around those islands, yeah, especially here in this anti-interferogram. Yeah, there's strong currents here. And also in the coherence, you can see there's some changing then because of the ambiguities that is introduced here into the interferogram. The level of ambiguity to signal ratio is again quite strong, just to challenge the algorithms. Could be a little bit better than we're at the case of harmony, but yeah, let's see how they perform. If we see the error, this is yeah, quite strong at those currents where we have the current flowing around the island. And applying the techniques also work to suppress, especially the slowly varying current, or the current is slowly varying spatially, and this can be then well suppressed. This is what we also see again in the median phase error plot. But yeah, for the for the technique here, because the scene is quite simple. The phase is not varying. You don't see a lot of fringes in this interferogram. So it is quite smooth scene. And then the plot over the coherence is to the right bottom is quite good. We can follow the lower bound for the estimation. But what we then see at some point, so for very high coherence, is that the algorithms somehow deteriorate a little bit more. And this is due to the movement of the sea, which is not really considered, especially for the IIR equalizer. It's harder, and we see that the hypothesis before that changing movement in the surface will have an impact on the algorithm. The other technique can cope a little bit better, but still there's some effects that need to be addressed. And if you see then for even more challenging case with about -5 dB of suppression, there's strong occurrence. If I switch back, you see there's even more biases, but these are more around like especially in those areas, and the overall coherence also dropped even more. But when we look again at the arrow maps of the two scenes, then we see again the coherence from the slowly varying currents can be well suppressed. But now both algorithms deteriorate here in the coherence plot. It's a little bit bad, but you can see what I mean. There's a strong deterioration, and we have to address those. Probably these are coming from the waves that are slowly, like very fast varying signals. And maybe we can achieve more with tuning, but also we have more ideas on how to improve the algorithms here. The last point is also validation with Ocean Simulator. You see here again, there's a scene with current and varying levels of ambiguities. Those can be well suppressed, but there's again the point of that we cannot really cope with this or like achieve the standard deviation according to the lower bound. And there's more now here, even because on the signal there's Doppler anomaly, of course, in the signal, and this also affects how the phase bias and how the removal of the phase bias looks like. So to conclude, the slowly, especially varying biases can be well removed. This will be then important for harmony. You can also imagine the Roselle with an ATI mode, something like this, where we could also implement those algorithms. Smooth surfaces are quite well suppressed. Then we have some sensitive to errors in the reference data, which makes the validation quite cumbersome here. But we see that there's also some more potential to improve, especially at high coherences. And we have some ideas how to continue here. And especially then surface velocities and motions need to be further addressed. So last example, I'm concluding and with the slide. There's now real data and real ambiguities. It's the scene from before, somewhere in Russia. You see again this, for example, this phase bias here from somewhere outside, further north. The IIRE, which is here now manually tuned to some area about here, because we have to account really for all the shifts, to maybe also take into account dams and so on to properly tune. I cannot really cope with this because it does not know how the ambiguity looks like. The MMSE technique shows some trade-off, but can remove, for example, this very strong bias. And some other extreme is this LSE technique, which is the ambiguity diversity, just with forcing it to be bias-free. You see there's an increase in phase noise, but the bias is completely removed. So thank you for your attention. Maybe the slides up for some questions.
thanks for this presentation and for the overview and the new techniques presenting for the coherent ambiguity suppression. We can just allow one question because we are a little bit late. Is there one pressing question? Otherwise, if not, should we continue?
There's time for a question. But no questions. No. Okay.
No.
Okay. Thank you. Okay, then we have one final talk in the session. Fernando Green Gandhi presenting another 3D deformation concept, which is already in development, if I understand well, the Chorus SAR constellation. Yes, please, the floor is yours.
Thank you very much. Good afternoon, everyone. Thanks for coming today. So today I'm going to talk how Chorus will enable the capability of measuring 3D deformation. For this, let's first take a look into an overview of the mission. MDA is developing Chorus. That is the next generation of our SAR mission. This mission, the goal is to provide continuity for current users of RADSAT-2 and to better address emerging needs of the intelligence market. But what's Chorus? Chorus is a constellation of dual frequency. Basically has two satellites. One is a C-band satellite and the other is an X-band satellite. Let's take a look into some of the characteristics of the satellites. Chorus C will be the leading satellite. This satellite is basically a fourth generation of RADSAT, and it's leveraging the best between RCM and RADSAT-2. This satellite is being designed, built, and will be owned and operated by MDA, and it will have broad area coverage with accessible SWAT of 700 kilometers. It will have capability for right and left looking, dual aperture and receive to have high resolution, larger coverage, step receive to improve noise and ambiguities, fast tasking and near real-time delivery, imaging of 20 minutes per orbit. Chorus X is being supplied by one of the leading commercial X-band SAR providers. It has sub-meter resolution, also will support right and left looking, and actually Chorus X will be trailing Chorus C by 1 hour. So these open possibilities for tip and queue also will support very fast tasking and near real-time delivery, and imaging 3 minutes per orbit as well. If you want more details regarding the mission itself, I invite you to see our poster session, and then you can ask there more technical questions about the mission itself. Some key parameters from the mission is the altitude. It will be 600 kilometers, similar as to RCM. Now the novelty here is that the satellite, it will be in a mid-inclined orbit, different from typical the near polar orbits that we are used to see, 53.5 degrees. So it will have an axis between plus minus 65 degrees. The local time at nadir will be variable. It will be decreasing by 20 minutes per day, and it will have a repeat cycle of 10 days, roughly of 10 days. And the trailing satellite will be phased by 1 hour. Chorus will support a broad variety of beam modes. It includes ScanSAR, StreetMap, and Spotlight. This is for both satellites, but the beam modes that will support INSAR processing will be the StreetMap and the Spotlight for both satellites. StreetMap for Chorus C will have resolutions of 5, 3, and 8 meters, and it will support single, dual, and compact polarization. Spotlight will have a resolution of 3 meters, and for the Chorus X, we'll have a resolution of below 1 meter. For Spotlight and for StreetMap, it will have a resolution of 3 meters, and only will operate in BB polarization. Now, let's take a quick look into what are the current challenges monitoring 3D deformation. So as we know, INSAR can only monitor deformation in the radar line of sight, and of course this derives in challenging interpretation of results, modeling processes can be ambiguous, difficult. We don't have enough information of the horizontal components of the formation. And many times, stakeholders and users require the 3D deformation. Now, to retrieve, in theory, to retrieve the 3D motion, we need at least 3 non-complanar line of sight vectors. And this typically can be achieved by using ascending and descending path directions, using different incidence angles, and also using right and left looking. Now, one of the problems we currently have is that mostly all SAR missions are in a near polar orbit and are right looking. There are some missions that support left looking capability, but with this current configuration, we only have sensitivity in the vertical and east-west component. Basically, we have no sensitivity in the north-south component. Even if we include a third viewing geometry, in most cases, we cannot resolve that. Here I'm showing an example of 2 ascending orbits, 1 descending orbit, just using a configuration, a typical configuration from RADSAT 2. And then I use the error propagation law, where I assign to a pixel a deformation of 1 millimeter per year for each of the components. And then I want to assess the precision when we decompose this deformation. And we can observe for this classic case, we have good precision in the east and vertical component, but pretty poor precision in the north-south component. Now, for example, RADSAT 2 supports left-looking. If we include a left-looking, definitely we can observe an improvement in the precisions, particularly in the north-south component, but still this precision is off 5 times by that 1 millimeter per year that we are looking at. So basically the hypothesis is pretty simple, is that the inclined orbit provided by CHORUS will provide a wider diversity of line of sights that can enable better monitoring of 3D deformation. So in the following slides, I will show you some simulations we conducted. The process is pretty simple, it's pretty straightforward. This was a feasibility study just to understand the sensitivity in the different components. So basically, we retrieve orbital information from RADSAT 2 CHORUS at different latitudes. We obtain parameters such as heading, incidence angle, and so on. On the other side, we build model of deformation, horizontal and vertical components of deformation. We projected those into line of sight. We added some noise, and then we performed 3D decomposition. So this was, we made many assumptions in this study. Phase is stable, zero spatial baseline, no radar effects, no topography, and so on. It's just to understand the sensitivity in the different components of when we compute that 3D decomposition. Now, one thing I want to show here is we are very used to look into the near polar orbits, how they are. Now, CHORUS is a prograde orbit, so basically the satellite is always traveling from west to east. So the yellow footprint is showing the ascending image. The red footprint is showing the descending image, and in both cases, this is right looking. This is at a high latitude. Well, at the mid latitude is 48 degrees. So this is very different from what we typically are used to see, right? And as you can see, the satellite is mostly looking toward the south. That's one of the main reasons it will provide that sensitivity in the north-south component. Also, another example of the high angular diversity that it can provide just by using different beams. And you can see there's the heading, that diversity in the angle that we can observe with the heading. Now, let's take a look into some simulations and the 3D decompositions. For this example, we utilize a point source, basically a MOGI source. This is a very simple source of deformation. It's used for volcanology studies and so on. So basically, we simulated a vertical deformation. And as you can see, then east-west and north-south component are showing horizontal motion, that it's converging toward the center of the image. So that's basically what we want to assess. We incorporated some noise as well. That noise has different wavelengths to simulate different components like atmosphere and other effects as well. And here, first of all, I want to show an example of a decomposition just using 2 orbits. Of course, this is an undetermined problem, but I use a minimum norm solution just to try to retrieve the 3 components and try to understand the bias on the different sensitivities for the different components. So in this example, at the top, we're observing the classic example, Radasat 2, ascending, descending orbit, right looking. It has 37, 47 degrees for the incidence angle. And this is a classic example where we have good sensitivity in the vertical component, east-west component, but not in the north-south component. With inclined orbits with porous, also we will have that same problem, right? If we use only two components of the formation. We can observe that at mid-latitude, we will have sensitivity in the north-south component in general, but now we lose that sensitivity in the east-west component. And we can play around with different viewing geometries. This effect, of course, changes as we go into lower latitudes. We can observe that with the main inclined orbits, we start gaining some sensitivity in the east-west component, but of course, we start losing sensitivity in the north-south component. So here it is where we need exactly three viewing geometries. We can observe in these simulations, top 3 orbits, just using torus orbits, center 3 orbits, combining near polar orbits with an inclined orbit, and the bottom even including more than 3 orbits, 4 torus orbits, and we can observe that in all cases we can properly retrieve that 3D deformation. Now here I'm showing a residual. We subtract from the decomposition the model that we incorporated, and basically we can observe that we have high residuals at this latitude of 48 degrees in the east-west component, and has less residuals. This residual is derived from the noise. From the north-south components is the lesser degree. Of course, the vertical has less noise. If we go even to lower latitudes, like 17 degrees, still we can retrieve that 3D deformation, but we can observe that the north-south component now starts having more effects, is more affected by the noise. The east-west component, it's improving, but the deformation is still estimated properly. If we go even to very low latitudes, so very close to the equator, same concept, right? We are improving the 3D decomposition, and yeah, the north-south component has large residuals in general. So this is something that we would potentially expect with different levels of noise and the type of deformation, how strong is this deformation, and so on. So here I'm just showing an example. We computed with different levels of noise. We incorporated different levels of noise, then we remove that deformation from, is exactly the residuals I was showing before for different levels of noise, and using different combinations at different latitudes. And we can observe that, of course, as we increase the noise, the residual signal noise tends to increase. That's pretty expected. Always, the less affected component will be the vertical component. The east-west component and the north-south component can change. This strongly depends in the latitude, and also depends which viewing geometries we use. For example, in this example, if we incorporate near polar orbits combining with the mid-inclined orbit, we have very low, in general, residuals, right? But in the other case, if we only use Chorus C orbits, we reduce the noise. This is the top right panel for the north-south component, but again, the east-west component gets degraded. Now, in this case, I didn't include any noise. What we are looking is at the distribution of all the possible combinations we can do for different geometries. Like the left panel is showing for just Radasat 2, just combining. This includes ascending, descending, left and right looking. In the center, combining Chorus and Radasat 2, again, ascending, descending, right looking, and the one in the end is showing 4 orbits and so on. We again apply that error propagation law to estimate the precision, and we can observe that if we use only Radasat 2 in the best case scenario, we can achieve, of course, this always has a left looking. The best precision we can achieve in the north-south component would be of around 3 millimeters per year, and we can see that we have very few options of combinations of viewing geometries. And there you can clearly observe how that precision gets degraded as we go toward the south. On the contrary, when we start combining near polar orbits with inclined orbits, the precision tends to remain at the 1 millimeter per year. Of course, it degrades a little bit when we go toward the south, but also you can see the wide variety of combinations we can have for obtaining that 3D decomposition. And the last example is showing that if we incorporate more viewing geometries, we can further reduce that noise. Finally, here I have an example. We saw one similar in the previous talk. This is a strike-slip fault that is generating basically pure horizontal motion. It's very classical that in geophysics and INSAR, if the fault is oriented north-south, there is no sensitivity to the horizontal motion. And in this case, I varied the orientation of the fault and then computed 3D the composition of 3D deformation, and we can observe that for all cases, for a case where we combine two near polar orbits and just by incorporating one inclined orbit, we can retrieve that deformation. Of course, this is very dependent in how strong is this deformation and how high is the noise, so those are things that need to be further inspected. So just some key observations. We need high diversity, angular diversity to obtain 3D deformation. Some advantages of using mid-incline and south and near polar orbits is that we can improve the north-south component at mid-latitudes, but this decreases, that precision decreases as we go toward the south. In general, we observe high precision of north-south at mid-latitudes, but overall, the east-west component has higher precisions. And the same with noise, same pattern is what we observe. So just overall summary, current missions don't provide enough angular diversity to accurately estimate 3D deformation. CORUS will provide this broader angular diversity with improved precision in the north-south component. There's definitely a lot of benefits by combining near polar orbits with mini-inclined orbits, so they will be complementary. And what is important that a proper acquisition planning will be required to minimize many of the problems like noise, temporal offset, and to obtain the highest precision we want in the north-south component. Thank you.
Any questions from the audience? Yes, Philip, yes.
Hi, thank you for your presentation. I was just wondering if you're not in a sun-synchronous orbit anymore.
Sorry?
If you're not in a sun-synchronous orbit anymore.
We will not have a sun-synchronous orbit anymore.
Yeah. Do you have?
So at the moment we have RADSAT 2.
Just can I finish my question?
It's still ongoing, it's still operating. Sorry.
You want to finish
Are
the question?
Are there ionospheric considerations? Because now you're going to have acquisitions during sort of peak solar activity or peak solar exposure.
Can you speak a bit louder, Philip? We can't hear you exactly. Yes.
Do you have ionospheric considerations?
Oh, ionosphere. I'm so sorry. Yeah, no, no. We incorporated noise. You mean in the modeling? We incorporated some noise that simulates short to long wavelength components of noise. But yeah, I mean, we haven't looked into that in a specific detail. Yeah, no.
Another question? Yes. Yeah.
It's working? Yeah. Thank you very much for your nice presentation. My question is related with the special coverage of the CORUS. Will be the same as RADARSAT?
Same coverage as RADARSAT? No, the coverage will be different. Since we're in a mid-inclined orbit, we try to obtain the most benefit from areas that are of interest. This is exactly those latitudes between plus minus 62.5 in latitude. So we will lose some coverage, of course, in the polar regions and territories that are located very far in the north. But in general, we have very good access in coverage for our market needs, of course.
Yes, Elena.
Yeah. I would have also a question because you're talking about chorus C and chorus X.
Yes.
Why you have chorus X? What is
So,
the purpose behind?
So no, that's a good question. So the main the concept of operations of chorus is tip and cue, and it will be heavily focused for maritime applications. So the idea is that we do broad area monitoring with chorus C using ScanSAR, and then, for example, we detect a target of interest, and then we can task chorus X to obtain an image of highest resolution at a specific location, and in that case we can identify that target and communicate these to end users. Yes, so that's the main concepts of operations. Of course, this is for maritime applications, but this easily can be applied, of course, to land applications. If we start observing an area that is deforming with chorus C and we require high resolution, I don't know, a bridge, we are observing some deformation in that bridge, and for monitoring bridges we tend to have need higher resolution to understand what is going on. Then we could task chorus X for that. So that's just an example. Same for pipelines and mining and all these types of the formations. Yes.
Interesting. Yeah. Very good.
Yeah. Thank you.
Yes, I would have another question.
Yeah.
You mentioned that, let's say, that it's already Chorus C it's already in development. Would be interested to know where you are in the development, and also what is the size, the foreseen envisaged size of the constellation for Chorus C.
The science for the
constellation. The size of the constellation itself. So how many satellites?
Oh no! At the moment, it's just we are planning just to launch Chorus C and X. Is just 2 satellites. There might be room to add more in the future, but it's something it's not defined. Not that I know.
Okay, and where are you right now in the development? It's currently being, where are you in which phase, or is it just study phase?
The satellite will be owned and operated by MDA only.
Yes, but where are you right now in the development phase in terms of, let's say, when are you plan to launch, and when?
No, we don't have that date. Still, it's to be defined. So launch date and.
Okay, so you're still in the feasibility phase right now.
We're in the design and build phase, but still we don't have a launch date. Not that I know.
Okay.
Yeah.
Okay.
Yeah.
Thank you. Okay, thank you very much. I think.
Yeah.
I think this concludes our session for our session, and also all the sessions of this morning. So there's a time for lunch, and I would like to thank all the speakers of this session. And this afternoon, after 2 o'clock, there will be Missions 2 presentation. So after the Missions 2, there will be the roundtable discussion. Thank you.
Great.
here. We're missing you. Yeah. Yeah.
Okay.
Shall we start?
Yeah. All right, so good afternoon, everyone. Welcome to the second portion of the mission sessions. We have 5 talks this afternoon. And after that, we have a roundtable that combines the discussions coming from the first session that we had in the second part of the morning and then this session. So we're essentially combining both sessions in the roundtable. So the first speaker is my co-chair. I'm Marco Lavalle from JPL, and I'm co-chairing the session with Nestor Jager-Martinez from Capella, and he's giving the first talk, Capella Space Repeat Pass INSAR Demonstration, Current Status.
Okay. Thank you, Marco, for the introduction. So I am going to give a summary of the effort that we are running at Capella to achieve an interferometric system. So something went wrong with the fonts. I think it was like short introduction to Capella. Can we fix the fonts? The fonts are, so the fonts are. It wasn't the case when I checked. Sorry? So here. Yeah. Sorry, what? So the fonts. Yeah, but yeah, maybe it will take too long. Maybe I can maybe remember on the title. It's fine. It's fine. That's okay. So yeah. So yeah. So I like this font actually. So thanks. So a very brief introduction to Capella. So Capella is building a constellation of SAR satellites working at X-band. It was founded 6 years ago. Engineering started 1 year after. So the satellites that we are using are small satellites in the 100 kilo to 160 or 80 kilo class. And we started delivering commercial products in 2021. Satellites are launched into mid-inclination orbits and also sun-synchronous orbits. So I will show some slides on that afterwards. And I would like also to announce that we have a new generation of satellites, which is called Acadia, where we have been doing upgrades to the radar system and also to propulsion systems. So the last satellite that we launched is Capella 11. It was launched 3 weeks ago. And here we can see the first light image, which was delivered just 1 week later over Japan. So this is Nagashima Spaland, an amusement park where you can distinguish, for example, here a giant wheel and roller coasters with high level of detail. So some information on some details on the radar system. So it is working at X-band. It is using a parabolic reflector antenna, 8 square meters effective area. The gain is 48 dB. We have increased the peak power. So in the previous generation was 600 watts. Now we have 800 watts because we have also increased the bandwidth. So from 500 megahertz to up to 700 megahertz, but this is something that can be configured. So it is a single pole system working horizontal or vertical by mechanically rotating the platform. So noise equivalent sigma 0 is between -21 and -10 dBs for shallow angles. It is able to acquire in left-looking or right-looking configuration. Duty cycle is up to 10 minutes. And something interesting is the very high dwell time that we can achieve, so up to 60 seconds, because we can mechanically rotate the platform. So for standard products, we are using between 20 and 40 seconds, which can deliver azimuth resolution already of about 5 centimeters. So the Capella 11, so the Acadia was weighing 174 kilograms. We upgraded the propulsion system, so we are using electric propulsion system, but we upgraded with respect to the previous generation. As I mentioned before, we are launching into sun-synchronous orbit, but also mid-inclination orbits, nominal altitude 600 kilometers, and it has been designed for 3 years lifetime. So the title should be like overview of the INSAR demonstration. So we have like, we are working in parallel in 3 different, let's say, activities. So the first one is related to INSAR performance. So different sources of the correlation have been analyzed. For example, signal-to-noise ratio decorrelation, baseline decorrelation, to decide which tube do we want to achieve, and also temporal decorrelation to decide also which repeat cycle would be interesting. For that, we have developed right now a very simple mission analysis tool and also an INSAR performance tool taking into account these contributions. Second part, the most challenging one, is the orbit control. So the goal is to achieve an orbital tube around a reference orbit. As I said before, we are launching into mid-inclined orbits, and the repeat cycles would be like 3-5 days, depending on the altitude of the satellite that we decide later. So for that, we had to develop tools for the generation of the reference orbit, and also all the automatization for the acquisition and the maintenance. And then the last activity is related to the INSAR processing and to the verification of the products. So for that, we want to verify the repeatability, consistency, what are the baselines that we are getting, also model the coherence. And for that, we have developed in-house an INSAR processor that can process pairs of images, which is actually a great source of information to give feedback maybe to SAR processing team, or to verify the coherence that we are getting. Also, since we didn't have a tube, or we are still working on that, we developed a tool to find in our catalog INSAR pairs that by chance have a small baseline. I will show something later. So when we start the demonstration, it will take about 3 to 5 months, because our goal is to acquire a time series of about 30 images over some predefined size that we have already. So I will focus only on these 2 points in this presentation. So something very little about performance. So this is just a modeling of the baseline decorrelation. So that should be the title. I am showing here what are the critical baselines for the bandwidth that we have. So we use 200 megahertz for strip map, 300 for sliding spotlight, and 500 for starring spotlight. And for the new generation, 700 megahertz. So, we have constrained, let's say, I think we have to constrain the maximum look angle to about 40 degrees, limited by signal-to-noise ratio decorrelation. And then if we want to accommodate, let's say, all acquisition modes, so 200 megahertz strip map is the one, which is like constraining the maximum baseline or critical baseline to about 5 or 6 kilometers. So here you can see for different tube radiuses, because we have been evaluating different ones, what is the expected height of ambiguity. And below you can see what is the impact on the coherence, geometrical decorrelation for different tube radiuses. So I have been listening also talks from URSS, and also talking to maybe to other users. We want all a small tube, usually for deformation. So taking a 250 meters radius tube looks ideal, because so the coherence is just impacted less than 10%. So this is what we are aiming. But of course, we can modify that later, making some experiments with larger bandwidth, or even seeing what we get. Oof, this one. This one is related to the mission planning tool. Mission analysis tool, so we are like building some tools to model the orbit. And here you can see, so this is a Google Earth representation of the orbital passes. This is just one example for an INSAR orbit at an altitude of about 620 kilometers. As you can see, the inclination is 44 degrees, and the repeat cycle is 5 days. As you can see here, so this is just one example of all the acquisition geometries that we can get over a site close to the equator. I think this is 20 degree latitude south. We have a very high diversity of line of sight, which is, so there was a presenter before from NDA, Fernando, that was proposing to use mid-inclination orbits. So I have just one plot on that, but if we plot, so everyone doing deformation is interested on horizontal deformation, and the bottleneck is the north-south direction. So what is computed here is what is the relative error for each component for north, east, and the vertical with respect to the accuracy that you can get in the line of sight. And this is done for different orbit inclinations. So this should be sun-synchronous orbit, and these are like inclined orbits. As you can see for sun-synchronous, so for low latitudes, we have a very high relative error. With the inclined orbits, actually, it is very similar, but we are like getting much better. Of course, there is a constraint on the coverage. So in the moment that we are using mid-inclination orbits, we are constrained to maximum latitudes directly related to the inclination. But what we can use is, for example, mid-inclination orbits for low latitudes, and then sun-synchronous orbits for higher latitudes. For east and vertical, so there is almost no difference between orbit inclination. So the gain is on the north-south. So as I mentioned before, so we have been acquiring in 2.5 years opportunistically interferograms by chance, so when the baseline was small. So here is an overview of the geographical location that we have of all the pairs, limiting the geometric decorrelation to 20%, also the incidence angle to 40 degrees, and in 2 months time frame. So we have about 780 INSAR pairs using the same platform. So the colors are Capella 2, 3, 4, so all our satellites. But we can also do interferometry mixing different platforms. So this is the same as before, but using, so this is the reference platform, but then we are like mixing, and then we have altogether more than 1,200 pairs to experiment on, to tune algorithms and so on, and to verify the performance. So this plot is just showing, so the most important one is the one at the bottom, so for co-platform and for cross-platform, how the perpendicular baseline look like with the temporal baseline. So we have a high variety of baselines. With that, I would like to show some examples. So I think I have altogether like 3 examples. So this is open pipe mining in, so this is in Australia, West Angeles mine. So all the images that I am going to show are radar top shadow down. So this is the range direction, the vertical one. This is azimuth. So this one has, so have been acquired, Capella 3, Capella 3. This is a co-platform, 40 days temporal baseline. And here I am showing an intensity overlay. So I think the mnemotechnics is red for flat. So for red areas, there have been a change. It was higher path scattering before. For blue is the other way around. So this is the coherence that we get, which is pretty correlated maybe sometimes with some changes in the intensities. And this is the interferometric phase once an external digital elevation model has been compensated. In this case, we are using Copernicus DM. So the acquisition dates were, this is 2021. So what we are seeing here, the fringes here, are actually related to dam change, maybe some troposphere, but the changes are so massive that we can see clearly elevation differences. Another example, moving to Europe, this is South Spain, Lebrija, close to Sevilla, agricultural fields. The same as before, this is the intensity overlay, so there are some areas with higher backscattering, varying. If we take a look at the coherence, we even see some correlation where there was a change before, also over here, I think, yeah. And the interferometric phase looks like this. So in this case, I have just compensated the ellipsoid. So actually, all these fringes are related mainly to topography. Yeah. If we compensate the digital elevation model phase, we obtain something which is much flattener, but of course, we have some atmospheric disturbances or maybe some soil moisture effects. I mean, everything that has been discussed on the other sessions. And my last example is, this is in Belgium. This is Antwerp. So this is the harbor. So here we can see very clearly when there are some vessels which are coming or leaving or remaining if they are in a grayscale. This is the coherence that we get. Over this area, there is some construction. So you can see also here some changes in the coherence. So there are some tracks, probably from vehicles. This is the interferometric phase, having flattened with the ellipsoid. And if we subtract the Copernicus DM, we see here, this is probably a dam change because of this construction. So we are getting things which are probably related so directly related to the changes. And I think this leads me to the conclusion. Yeah, I think this will help, yeah. Yeah, so Capella satellites are able to produce coherent imagery, and right now we have been able to do that when the orbit was favorable. We have more than 1,200 coherent pairs, which have been acquired just by chance. We have shown some examples of interferometric phase and also coherent change detection. The level of coherence is as expected for the noise equivalent sigma 0 that we have and for the baseline that we had. Mid-inclination orbits will be, I think, very relevant to retrieve the north-south direction, especially for, I forgot to mention, but the swath is pretty narrow, so we have 5 kilometer swath. So the use case will be like infrastructure monitoring, landslides, and things which are small, but when we have horizontal deformation will be, I think, relevant. And we are still working towards achieving an INSAR orbit with a tube of about 250 meters for the upcoming satellites. So thank you.
Thank you, that's good. So we have time for one or two quick questions. There's one over there.
Yes. Hello, thank you for your presentation. I would like to ask about the last point. 250 meters is for satellite or for many?
Yeah. So right now we are focusing on one satellite. So we want to achieve the INSAR orbit for one satellite, perform the demonstration, see how much attention do we have, and then in the future, so Capella should decide how many satellites are in an INSAR orbit.
Okay, in the same 200 tube, I mean, all of them.
Or maybe
how many you decide?
Yeah, or maybe based on customer requirements or needs, let's say.
So it will be kind of flexible.
Yeah, so if you have some feedback to give, please let me know.
Thank you.
Okay, perfect. So if there are no more questions, we can. By the way, we have time in the roundtable discussion. So thank you, Nestor. So the next speaker is Shoan Kin. His talk is going to be a first glimpse on the interferometry and multitemporal capability of the Chinese Gaofen 3ABC constellation.
Okay, let me try this first. Okay, great. Okay, thank you, Marco. And good afternoon, my dear colleagues. And today I'm very happy to share you some of the recent advances from the Chinese Gaofen 3 SAR satellite mission. So my name is Yu Xiao, and from Northwestern Polytechnical University of China. And this is a joint work between many divisions. Okay, and a little bit about the background. The Gaofen 3 belongs to the Chinese high-resolution Earth observation system project. So this is similar to the Copernicus with the SAR and optical and others. And Gaofen 3 is the first Chinese civilian SAR satellite. And so as you may notice, it's actually being launched quite a while ago in 2016. So the good news is last year, we are actually having some more advance. So we have the 2 more satellites in the orbit, the B and C. And now this year, they are all out of the commissioning phase. So now forcing a constellation. And so in that sense, so first of all, just a very brief introduction to some of the specs. I here have 3 typical C-band satellite. And as you probably can see, we are actually learning a lot from the one is the Sentinel and the other is the radar set. So all the since the first one is more or less a POC, a proof of concept. So basically, we use quite similar configurations. We are having a more heavy satellite because we have more peak power. Okay, and here you can see that we are really learning. Mostly from the radar set for our first one. So we have a lot of mode. So for example, there are different modes for the strip map. This is a little bit hard to see, but just to give you an idea. And so for the wide swath, we use the ScanSAR for A, but then for B and C, we're actually switching to TOPS and wave mode and spotlight, etc. Okay, and as some of you guys may probably feel that the Gaofen 3 is not really exposed to the INSAR world since it's 7 years of operating. So as you see, the main purpose of the first one is, except for the POC, is mainly for the, say, maritime or the disaster, so which means that we're basically just using the amplitude for the analysis. So interference is actually never one of the first major purpose for the first satellite. However, since now we are having a constellation, so this is coming into the play, and we are now seriously considering that what we can do to improve the INSAR capability for this constellation. So for that purpose, we're carrying out this research, and there are 3 main purposes. So first, we want to understand, so from the first satellite, if we can do INSAR, and also for that matters, the multitemporal analysis. And if we can't, then are there any parameters we should improve? Or if we can, like to what extent we can do that? Okay, so this is a basic idea of driven behind this research. And so the second is the process. Actually, we are running a pretty standard INSAR process because we first just want to understand how well we can do INSAR and multitemporal analysis for the Gaofen 3. So basically, the only thing that I did is slightly different from the other regular sensors is trying to do this so-called stitching, because bear in mind, we're not really planning for the INSAR in the first place. So the cutting of the images are kind of random in the beginning. So in order to have a better, larger coverage, especially for the multitemporal purpose, we need to concatenate the adjacent scene. But I mean, this is strip map. This is not TOPS, so this is even easier. So there are multiple ways we can do that. And so this is just an illustration. And then besides that, we are just basically running very standard things. So for example, in the pre-processing, we're doing the co-registration with the cross-correlation. So by the way, just to mention, because our POC, the first satellite, is not actually providing the precise orbit, so there's only the onboard GPS. So that makes it hard to do the geometric co-registration, but that's no longer going to be the case for the constellation. And then the stitching, and here I mentioned remove of some of the phase ramps, which I will not go into detail, we're still working on that. And then for the multi-temporal part, it's basically very standard. And we're running only a PSI here, so no DS or phase closure fancy stuff at the beginning. And then we're doing some post-processing just to do some evaluation and comparison to understand where we stand. Okay, so here I'm very happy to show you some of the results. So let's start from INSAR. So here's like a stack, and this is Spotlight. This is just somewhere outside Beijing with a Spotlight track. And here is interferogram and coherence. And you can see that we get fairly good coherence here. And you can basically see the structure of the, so for some of the less coherent image, you can see the outline of the roads and small towns, right? So that's pretty nice. And then we're also running some more experiments for the 3 satellite system. So here I didn't really get a lot of data, but out of all the data I have, there's actually some quite good results, I would say. So for example, we have different modes. The first is Spotlight, and the second is Strip Map. So you can see that Spotlight is definitely giving some more details. You can see the road and the house, right, because of the DEM error. And then we have the different satellites. So the second one is the Golfin 3B, and the third one is the Golfin 3C, and the third one here is a mining site. You can see clearly the mining site because of the DEM error. And then the last one here is a cross interferogram between the 2 satellites. We have the Golfin 3 and Golfin 3B. Yeah, so this one's actually not so optimized since the normal baseline is almost 2,000 meters. But with a 6-day spatial baseline, you can actually still see a lot of very good coherence on the south part. Well, maybe north. I forgot this is descending or ascending. Anyway, the lower part of the image. And the upper part is totally decorrelated. This is because this is actually a deserted area, so you're not really gonna get any coherence in the desert. Anyway, so this is promising. And just to convince you that I'm not picking one good interferogram out of 100 crappy one here, so I'm showing like a network of, so a bunch of more interferograms. So this is a stack that I later actually use for the multi-temporal analysis. So there's 25 images altogether, and I'm basically showing like, this is either a network, a full network, or close to a full network. So you see all the interferograms and the coherence map, you see the good ones and bad ones, but basically you can see almost all of them show some sort of signal. And I mean, this is actually a quite large interferogram. This is like 20,000 by 20,000. So this is, the thumbnail is not showing details, but yeah, just to convince you that we're actually having this regular capability of generating interferograms that is carrying signal. Okay, so actually for myself, INSAR is not as interesting as the multi-temporal analysis because it's always giving more accurate details. So here I'm showing another, the stack that I just used previously. And this is a basic configuration. So by the way, we actually, so you can see the altitude for the first one is actually quite high, almost 800 kilometers, which means the revisit time is a little bit higher, 29 days, 1 month. So similar to the first ERS MVZ system. And here you can see that the normal baseline is actually not so optimized. We have a couple of pairs exceeding 1,000 meters. And actually I cheated a little bit because I threw away a couple of interferograms with 2,000 or above the baselines because they're really not useful. And also somebody can see that there's actually a big gap between the March, almost April of 2021 to the March next year. So this is actually not so good for a multi-temporal analysis, but we are processing urban areas, so probably fine. Okay, so this is a basic configuration, 25 images, 29 days. So you probably already imagine the kind of results in your head and see if this matches your imagination. Okay, so this is my results, a very preliminary one. This is the city of Beijing. And so this is saturated to plus minus 20 millimeters. Yes, and this is the time span of 3 years. Okay, so when we have this kind of results, the first thing that pops up in my mind, or probably also yours as well, is this results legit, or how do we validate these results? So naturally, we compare it to the Sentinel, right? Okay. So this is the Sentinel results. So I flip forward and backward. And you can see that they are basically matching quite well. And so this is Sentinel descending, so the same, both descending. But unfortunately for the Sentinel descending, we will have B. And so the last acquisition date is November 2021. So the time period doesn't really match, but it still matches pretty well. And so this is the other processing using the ascending track because we can have the same time period. So you can see that they are still matching quite well. So there are some discrepancies, but basically since I'm saturating already to 20, so I think it's pretty good. And the next step is to show some statistics because it's not good enough to say that it looks good, okay? So one thing I always keep an eye out for is the point density. So here you can see that for the Sentinel ascending and descending, we basically have a similar point density, which is 300 points, more or less. And then for the Golfin 3, we have almost 20 times the number of points in terms of density. So this is actually out of my expectation in the first place. Of course, there are some details that I didn't really explain. For example, how I select the threshold for the PAS, stuff like that, we can discuss later. And just to have a reference from the EGMS that people are discussing nowadays are popular. So in the EGS, there's a quality control matrix saying that for the urban area, class 1.1.1, 2, we should have like more than 1,000 or 5,000 measuring points. So here we're definitely somehow achieving that, although somebody may say, okay, you should further check the quality of your points with more rigid measurement, and that is true, and that is probably what we're gonna do next. Okay, and I also run a very simple correlation analysis for the velocity. So on the x-axis is always the Golfin 3 estimated, and on the other axis is the Sentinel. And we can see we are having actually quite good, I would say, statistics here. On the left-hand side, we have R square of 0.87, slope close to 1, which means they have a 1-to-1 match. And RMSE for both cases is almost 2 millimeters, which means if we take the Sentinel as a reference, and then the accuracy of Golfin 3 comparing with this reference Sentinel is almost 2 millimeters per year, which is, I would say, quite good, considering we have only 25 images with really crappy baselines and only 25 images. And one thing I want to point out is that the images to the right, which is the comparison between the descending and ascending, is showing, so first of all, slope is not 1, it's like 0.7, which means that the one measurement is always underestimated or overestimated. And also the R square is a little bit lower. And one possible explanation is that I know for a fact that in Beijing, there are a lot of very complicated horizontal movement and also vertical as well. So in this case, because for this comparison, I actually kind of use a simple way just to convert LOS into vertical and compare the vertical, which is not actually legit when you have a very strong horizontal movement. So this might explain why on the right-hand side, ascending and descending didn't agree so well comparing with the left. But I mean, on the left-hand side, you have both ascending and they agree really well, which is a good relief, okay? And just some very simple example of the details. As we know, the power of the high-resolution data is that they can show to a very detailed local displacement. So for example, in Sentinel, you see a couple of points with a displacement, but in the high resolution, either Golfin 3 or the other excellent satellite like Terasar or Cosmo, you'll see the details. So this is also the case here, we can see. So only with 25 images, we're able to actually achieve that, which is, I think also I would say the noise equivalent sigma 0 is really playing an important role here, because I know for the Golfin 3, the NESE is around -22 to -28, although we still need to do some more experiment to validate that. Okay, and one last very thing that we always discuss is the baselines. And so we're also wondering, like, I believe there's a balance between how you set the baseline and the lifetime of your satellite. Because if you want a better baseline, you need more like orbital control, more burn more fuels. And now we only have, before we only have one satellite, and we also want a very deep stack for the INSAR. So this is also very important for MT INSAR. So it's just a matter of finding the balance. And for our purpose, I here select 3 typical land type, the PS and like a PS plus DS, and then a vegetated area. And I want to see that if the PS point, how PS point decorrelate over time. Well, theoretically, they don't decorrelate over time, but so this is the plot. I select a small area, and I generate all the interferogram pairs, and then I plot them out. The x-axis is the temporal baseline, and the y is the normal baseline. The color shows the temporal coherence, and spatial coherence, sorry, the average spatial coherence of this small area. And as you can see, for place where you are dominated by PS point, they really don't really decorrelate. So this matches well with the theory. So in this case, you can see that even with the temporal baseline of 1,000 days, and with the normal baseline of 800 meters, you still get a, well, fairly good coherence, which can be used for PSI. I would say definitely not for DS, but for PS, okay. And then if we have an area with some buildings and then some rural areas as well, and you can see it decays a little bit faster because here we are getting the average spatial coherence. But still, in this case, if we choose a temporal baseline of like 200 days, and then, yeah, okay, I'm almost done. And then the spatial baseline of like 500 meters, I would say it's okay. So yesterday, Urs from Gamma mentioned 500 meters for the ISI project. So in this analysis, I would say 500 or 600 could probably do. We will need to run more experiments to really calculate this number. And for the vegetated area, there's really nothing C-band can do. We'll just go for the L-band. Okay, and yeah, I'll skip this. Yeah, just one quick thing. So we also see the baseline for the other missions. So for example, the CSK is, so this is quite old data. This is probably from 5-6 years ago, but just as a reference. So CSK is from -1,000 to 1,000, but we already see a lot of beautiful results with CSK. So I think for PSI, we can live with that. Okay, so brief next steps. So there's 2 things for the next step to consider. So the first is, people are always asking me, like, how do we share? So Golfin 3 seems quite mysterious to people. You don't get the data, you don't get the, and one other thing is that you don't also get the tool. So for example, Snap only supported Golfin 3 in version 9, which is very recent. And we also tested it, and there's actually a lot of bug in there preventing you from using that. And yeah, and also I have to say Java is really hard to, for people to contribute. Anyway, but we're still aiming at pushing up the tools. So for example, all our processing here is done in the open source world. So we do the co-registration with the Doris repo. This is the TU Delft in-house processing tool, supposed to be the next generation of the Doris. We're working on that. And then for the time series part, thanks to my friend Richard, who developed GCoris as an open source tool, we are working all our modules based on this. And now it's still not available, but because we're still working on that, but later on we are going to open source everything for people to facilitate. People can also do their own research. And sorry, 1 minute. And one last thing, just want to give you some ideas of the current status of the Chinese mission. So in the past, we really learned a lot from ESA and also MDA and other facilities. And yeah, so we're basically still learning, but this couple of years, we're actually making some progress. So for example, the Golfin 3, we now have a constellation, except the multi-temporal part. There's also, for example, we already have the ASI support. This is for tracking the ships. So this is already there for the Golfin 3 BNC. And we have the TOPS mode, and then we have the onboard data processing. This is basically the focusing onboard, so save some time. And also we're considering INSAR as a major application for that. And also the other day, somebody mentioned also the Lutan series for the, it's already out there, it's launched, it's out of commissioning phase. This is a high resolution L-band system, biostatic, full pole, and it's specifically designed for INSAR. So this is also going to be very interesting. And we're going to launch X-band biostatic mission next year, hopefully. There's still no name. We probably have a code, I have no idea. So this is similar to Tandem Max. And if all this above, you think, oh, this is boring, I already have this, then one last thing, this is going to be interesting for all of you. So last month, we just launched our first geosynchronized SAR satellite in L-band. And so it's supposed to be 20 meters resolution L-band, and we're supposed to do INSAR with it as well. So hopefully for the next Fringe, I'm going to bring you some news for this L-band geosynchronized system. And so take home message for the process. We are seeing some promising results from the current Golfin 3. And for the next steps, we are going to do more experiments. We are going to focus more on the INSAR part. And we are going to also join the open source world in terms of both the data and the tools. And that concludes my talk. Thank you all.
Thank you very much. We have time for one very quick question.
Yes, thank you for your presentation. I would like to ask a question that before 10 years it was asked by all of new satellites. What about your policy for the data? It will be open for the public, for the scientific community. What are you planning? Thank you.
So many people ask me this question, and so the honest answer is I don't know, because I come from university, and this data is, the policy is being made by all these other authorities. But I was talking to them, and it's actually something I didn't expect. So some people may think, okay, they don't want to open the data because of some, like, I don't know, politics or some other things. But the thing is that they didn't really have a plan. That's my understanding. So for example, for the Golfin 3, they're not even sure if we can do INSAR. So that's why they are hesitating in if we should open the data. Like if we open a bunch of crap to people, that's like wasting other people's time. So in that sense, I'm also trying to push this forward. And actually, we are quite open to find a way to open the data. So actually, we already have this website that you can do all the queries for the data for Golfin 3 and Lutan all together in a system. And so, yeah, I'm also looking forward to the next steps, see what we can do here. We definitely want to find a way to open the data and share and ask the science community to work together with us.
Okay, that's very clear.
Thank you.
Thank you. And so I see other hands up, but we move to the next speaker, and there will be time in the roundtable session to ask more questions.
Yeah, so the next speaker is Irena Heinzek from ETH Zurich and DLR. The title of the presentation is the KEA band interferometric radar mission proposal for cold environments. Please, Irena.
Thank you very much, Nestor. Yeah, so I can't really talk today about a very exciting mission that is already launched and show a lot of great data, but what I will do, I will present you a new mission proposal that we have, and we would like to submit it to or we are already in a process to submit it to the Earth Explorer Call 12. And this is in principle what I'm showing today. So the main idea behind SCADI is to measure or to quantify and to assess dynamic components or dynamic processes where we estimate static and dynamic components of the topography. And for this, we're suggesting to have a single pass INSAR interferometer in order to estimate more precisely topographic variations. The main team, your science team you see here, this is composed by experts from permafrost area, from snow areas, from modeling parts, but also from some field observations, so people doing this, but also people from system design, instrument, and mission concept. We have two industry partners, so this is Airbus and OHB. Let us go a little bit to what are the primary mission objectives of this mission that we here suggest. So you see already this is a landscape that you would like to observe. This is a permafrost landscape, and on this permafrost landscape we have certain contribution that we would like to measure. It is a very highly complex, I would say, nature landscape that we have here. And one important parameter that we would like to measure is in principle the gradual but widespread regional topographic change in terms of elevation change, where we need very high vertical accuracy over a multi-year time period. This is everything that you could do potentially also with INSAR, but here in this case, we would like to use single pass INSAR where we have a generation of digital elevation model in order to subtract a high resolution but also high precise digital elevation model from the other one, so doing differential dams, and with this differential dams to see the really widespread movement of the Earth's surface when some melting is ongoing. So the second thing that we would like to do is also to observe very rapid changes. So not only the small, gradual, smooth changes, but rapid changes. These are mainly local features that we have. And here we have very strong seasonal and high seasonal differences, so very dynamics in the season. And for this, we need more high spatial resolution imagings. In addition, we think, and this is shown by several publications, that you have a strong impact of the snow cover on this degradation also of permafrost, or even the properties of permafrost. So therefore, what is also very important to measure the snow thickness distribution. And as the last point, what is also important in this image is actually the vegetation on top. So the vegetation on top is also something that we like to measure and to estimate, to characterize it a little bit more in terms of structure and productivity in order to be better predictive also what is happening in the ground. So that's the main objective. We have also secondary objectives. You will see this later on. But what is the science rationale behind it? Up to now, there's no dedicated mission for permafrost observation, so it doesn't really exist. So this would be really the first mission, if it would be supported, let me say, which is really dedicated to permafrost changes in the permafrost. The problem is also, in addition, that permafrost is more, or everything related to permafrost is also very strongly related to subsurface dynamics. So it's not something that you see on the surface, but everything is happening is below the surface. So the remote sensing, or this is what we like to do, is in principle the observation that is on top, but with proxies or indicators that are giving us information about what is happening beneath this, the surface. Another thing that is also important actually is that it has been, in 2022 in science, the climate tipping points has been defined, and permafrost is one of the climate tipping points, which means if once, due to degradation of the permafrost and due to the climate warming that we have, if there is degradation already ongoing, there's no point of return anymore to say, okay, we can replace it, or we can remodel it, or we can, preserve this situation. So therefore, everything that is happening now and is degraded, we cannot go back to original conditions. Another point, which is also important, that the prediction in the future is really quite dramatic in terms of dramatic permafrost degradation. This is a model assumption that you can see how strong it's really degraded or will be degraded in the years. I think that's a prediction to the year 2100. However, what we would like to have is in principle a systematic, consistent remote sensing observation system, or mission in this case, which is consistently observing this kind of degradation, is quantifying them, and then the second thing would be to integrate them into Earth system models. So that's the main idea also behind it, to have it also as proxy information for this more global Earth system models. And then, in principle, these Earth system models can do some climate impact or have, in principle, some prediction into climate impact, social implication, but also habitat change. Why I'm saying this and why I'm coming to this, that digital elevation model could be very helpful for it. So I have an example here used from TandemX. Everybody knows probably now after this conference, TandemX is producing very high resolution digital elevation model with a certain accuracy in terms of vertical accuracy, in terms of height accuracy. So we are around in flat areas around 1 meter, so height accuracy, which means everything that is changing in a smaller scale than 1 meter change, right, you would not observe this. So but what you see here, this is one of the examples, which is a very local focused change, which we call retrogressive thaw slumps, which is a very abrupt change, seasonal, very dynamic. And what you see here is in principle the feature of this RTS, we call it shortly. It's a feature, sorry, you see it here on the picture on top. This is a feature which you see, where you have a strong head wall and in principle, the material, the earth material that is in principle deposited in front of this head wall. And this you see very nice in these images. That's a round shape here over different time span, this difference or height changes that you can see. And if you look now to the plot, you see also over the time, the height changes are quite drastically from 2011 to 2017. If you'd like to know more about this, in principle, go to a poster. We have a poster here from Katrin. She's sitting here in front, so you can still get more information about the process and the method that we're using in order to extract this. However, we see we have degradation ongoing with the years, which is very strongly, but it's not only one feature, not to cheat also on these, but we have quite a lot of these features, so it has an impact. So what you see here, these are the blue dot points. These are all retrogressive thaw slump that has been identified. This is only now over a Canadian area, the Mackenzie River Delta and also Bank Island. And what you can do, if you know once how much is changing in terms of meters, then you can also transfer this using a power law relation into kind of volume changes. And that's important. If you know volume changes, then you are also aware of knowing also, let me say, the type of soil, then you know also how much CO2 and how much gases are released in the same frame. So therefore, this is a very important issue. However, we found also out on a certain time, between certain time frames, that this is very strongly impacted by global warming. You see on the TP1, sorry, this is here, on the TP1, this is a time frame between 2010, 11, 12 to 16, 17 over the Pioneer Peninsula. And these are the same features as you have seen before. So these are the dots where we have this RTS. And there, some of them can be located. But if you go now to the second time frame, where we have between 1819 and 2021, you see how much in terms of features are increased, so how much of these RTS are progressing, and also the area has been changed, which means also the amount of things are really increasing. So you have a 42-fold increase in volume change rate, and this is only because we had in 2000 a very, very hot summer, over this permafrost region that we have here in Russia, and therefore we have this very, very strong increase. So it has a strong impact, and we like to measure this really consistently with a mission. So now you can ask, why not doing this with TandemX? Because I show already results with TandemX. As said before, TandemX is not the accuracy that is really needed in order to measure this. So what we need is really more high, precise digital elevation model with a better accuracy in terms of vertical accuracy. Yeah, and this is something that is still missing today. We have a strong gap here, and we would like to go forward on this. And TandemX is also not doing consistent imaging of all permafrost areas, right? Because we have some restriction in terms of duty cycles. But this could be something that is really dedicated to it and could be more intensively looked at. This is a table. I'm not going through all the table, probably just to capture what is most important are the requirements. These are the accuracy, the vertical accuracy requirements, which is here going between 10 centimeter, right, to 50 centimeter, or even to 1 meter. So depending a little bit on the primary objective that we have. So for this slow moving, we need higher accuracies, but it's lower spatial resolution. For the small change with abrupt changes, where we need less height accuracy, because the features that we see are stronger in terms of stronger variations, in terms of topographic variation, but high spatial resolution, and so on. So probably I just figure out one thing. We also measure snow height changes, and the snow height changes here are not done in terms of really covering the whole area, but is more meant to have samples. So therefore, we would like to have here a gridded sample over the whole area, the whole global land surfaces, not only over, let me say, northern parts. So just for the secondary parameters, because this is what I haven't mentioned before, is vegetation structure is one. Sea ice topography is also very important to be measured, and it's a very also hot topic in terms of if you have also snow cover on top. But it also can be used for geohazards for any kind of landslides, rock falls, mining, and so on. And what is also meant with this mission, we would like to have a kind of base map, a global digital elevation model, once covered all land surfaces, in order to have it as a base. So the main mission requirements would be now to have at least a swath width of 50 kilometer, a spatial resolution of 1.5 meter, and said a repeat time as frequent as possible. And as said, also we suggest to have a single pass interferometer. Why Ka band? Because we are coming here from, I was talking about X band and before, but now we are switching to Ka band. So X band because I show the results of dynamics, but here this is really for Ka band, and the main idea really here behind is to have less penetration into the permafrost area in snow regions. So less means really less as X band, so which means also being more precise in the digital elevation model. Also, what is very important here, the concept of the spacecraft is probably also cheaper, I would say, because the weight and the size is smaller. And we see a lot of synergies with other missions here, because we would also generate a kind of base map and a very, very high vertical height resolution, which is very important. However, this is still very challenging if you have these requirements on the mission. And this means, in principle, you have always a trade-off between high spatial resolution and coverage, right? This is always which we are dealing with in any kind of the missions. You see here two kind of frames. So the one is, you see here the azimuth spatial resolution that you compromise by the swath width. And we are now here heading to future SAR mission, where some of them we know already. We have this concept of the score with scan on receive, and the same idea here behind is also to use the same technique to keep high spatial resolution, but have still enough swath width available. Okay, this scan of receive has been already presented quite often here. This is the industry that is working in the moment on it. It's Airbus and OHB, and there's several ideas how to realize it, not only on score, but also staggered SAR. We are thinking also to implement the frequency scan, which is a very new idea, scanning different frequency through it, which is called F-stack, or even potentially to have a photonic beamforming available. Yeah, so the mission characteristic I was already saying. So the main idea why we would like to have a single pass interferometer, which is not just on one instrument, but having really two satellites, means to be more flexible and having the height of ambiguity variation. So we would like to have one which is 30 meter and the other one 50 meter. So this means really two different set of baselines in order to comply with this vertical height resolution that we would like, or the accuracy that we would like to have. We have done first simulations because there's not so much data available in terms of looking really on the performance, in terms of getting the height that we would like to have. So what you see here, this is now the performance table for the digital elevation model, and everything that is green on this side here means that the target and the goals are reached. Everything that is more grayish, which here, for example, the goal is very restricted, we are not reaching it completely. So that's still something that we need to compromise here, but what is at least possible that we are reaching the goal. However, these are simulations, and it's pretty clear we would like to have some data in order to also prove this concept and the performances. Yeah, the main product, I said already, out of it would be a differential digital elevation model, so something that provides a change between two digital elevation models. It would be the vegetation topography and the structure. We would like also to go for a product which is called kind of density of snow or grain size, so it's more the density of snow using polarimetry in this case, and also to estimate penetration biases. That's something that is also very important in order to really keep up with a good height accuracy that which we are heading to. Okay, we have some temporal sampling requirements here. So what we have is big permafrost regions, and these are mainly our driving requirements that we have. But then we have also over snow region, we would have topographic changes that we would like to measure too, and this on the weekly basis, so much higher temporal resolution. And then more on a global scale and can take a little bit longer is in principle the global surface elevation. You see the ROE mask that we are in the moment working with. So these are the regions of interest, which are mainly the permafrost region on one side. On the other side are the land ice. And we were now looking for everything that is above, let me say, 60 degrees latitude in order to see how we can cover it if we do some kind of mission analysis. So up to now we had a very low orbit with 590 kilometer, an NES set of 17 dB, as said before, and this is now calculated with one height of ambiguity. So we would have different mission phases. This would be the idea. So in the first one, we would go from May to October, where we would cover all the permafrost areas in two different incidence angles. So the first month between, you see it here, 27 to 32, or 32 to the second month, 32 to 36. Or what is also possible in principle to use a 60-day repeat time where we use only one certain incidence angle range. The second mission phase would be then from November to April, where we are only focusing on snow estimation, so where mainly the snow needs to be covered. So that's another, and then in principle the third one would be the global dam. I have only some smaller plots now about the mission phase, just to show that within this 60 days, so first month and the second month, we would have a really global full coverage of all land surfaces, as you can see here quite well. For sure, the northern and southern parts are, let me say, more frequent covered than the rest. In the mission phase 2, where we only do gridded sampling, which means we are not doing full coverage, but we are doing a grid sampling. Here we see, you see already that the coverage is a little bit reduced, but we still get quite good estimates also over the equator, and everything that is north is much higher sampled and covered as things which are going more to the mid-latitude. Okay, just going a little bit to the programmatic elements. So we think this study is really a missing mission up to now in worldwide set, not only because, I mean, there's a lot of sensors available, but nobody's really dedicated in terms of permafrost. And in principle, we think that SCADI can really cope with this ESA Living Planet program for the cryosphere, solid earth, and the land surface, and has also a lot of societal issues that can deal with in terms of climate, diversity, food, water, natural energy, and hazards. And we think also it's a unique mission proposal because it has a lot of complementarity and synergies with other missions, which is great, just seen here already and also already mentioned. And as said, the main driving products that we have this differential single pass measurements, or this other acquisition, and having really the sensitivity to very, very small structure and dynamics also of very, very small height changes. Yeah, so neat and useful excellence, yeah, we think it's missing, as said, just because it's an urgent matter in terms of permafrost degradation. It's going very, very fast and rapid in the last year. You have just shown the one example that I was showing with TandemX. So from this point of view, we really think this would have a very, very great impact and value in this community to know more and quantify more what are the changes. Yeah, and in addition, we say K-band is not so unknown to us, even though we do not have really remote sensing data so much available. There's a lot of other sensors, ground-based sensors that are available that are already measuring snow parameters, but also technology has been already involved for different other regions, not really for permafrost or for satellites, but there's a lot of studies already ongoing at ESA that could also support, in principle, this innovation and also development. So my recommendation on the next steps here is, in principle, there's really a strong need of Ka-band data to really support the simulations that we have done, so that's important, which means we have a lack of data, which means also it would be great to have some support in terms of airborne campaigns. There's a ground-based sensor available, which has this frequency from WSCAT, from gamma remote sensing, so they had acquired a lot of data over snow areas, and we are now currently on the way to investigate these a little bit more. And as said, we are now in the way to do the submission, because the submission deadline is actually end of this month, so we are really heavily now working on the proposal generation. Probably just one last outlook. concerning airborne campaigns, there's also other sensors which can do Ka-band nowadays, but also DLRs is working or has already developed, let me say, Ka-band Pol-INSA demonstrator. What is really nice on this one is it has in principle for a cross-track antenna position, which means you can get at once 3 different baselines. So you have in principle 3 baseline acquisition in one shot. So when you do one acquisition, so that's great. And what is also great that you have fully parametric capability also in this area. So just as an add-on to probably things that are anyway ongoing. Yes, so that's in principle my last slide, and yeah, I'm open for any questions that you may have.
Thank you, Irena.
So we have time for one quick question, please.
Thanks. Very nice talk. Well, first off, NASA, JPL has a UAV SAR Ka-band that does topography, so there are some data out there for especially Greenland and places like that.
Paul, can you speak up with your microphone?
Okay, sorry.
Yeah, better.
But my main question is, so you mentioned, for example, Solid Earth or some of these places where you probably are getting less acquisitions. How would you be able to do differential DEMs if it's, I mean, does it have the agility to go back to places it's already measured, or is it simply in this kind of rigid coverage?
If I understood the question right, so in principle we are now heading to have all the cold region area covered, so fully coverage, with a single pass interferometer. So you get for each flight, in principle, a digital elevation model. And then you come repeatedly over this area, and you can see then the change, actually, from one digital elevation model to the other one. And you see, because it's so high, the vertical accuracy of the height is so high that you can see really small movement changes.
Right, no, that I understood, but my question is about on any given point on the Earth, especially at lower latitudes, what is your revisit time?
Yeah, in the moment is it's depending what you're looking for. In the moment we have, I mean, if you look globally, it takes a month. This is what we have, the 29 days. That's quite, let me say, it's once a month in principle. You get an acquisition, which is on a global scale, but you have, because you have more flyovers in the northern area, so you would have it more frequently, right. But probably with different incidence angle ranges.
Okay, thanks.
Okay.
Okay, thank you.
We can move to the next presentation given by Yuval Cohen, Quality Assessment of ISI and SAOCOM INSAR data within the ESA-EDA Plus activity.
Well, hello, it's actually Jorge Ruiz who is presenting today. And well, I would like to start maybe with a small, maybe call it apology or as a small note, saying that the assessment of the INSAR results for ISI or for SAOCOM are going to be a bit scarce. But it's a bit very good opportunity to present all the activities that we have been doing in EDAP for the past, now, I believe, 3 years or a bit over. So I guess it's nobody's surprise that during the past years, this amount of small satellites led by all these commercial companies have increased significantly. And I guess during this past few days in this conference, and even in today's session, we have seen all the science and all the exciting things that they are doing. And I think this speaks volumes about the importance that these new constellations of satellites are going to have in the Earth observation international strategy. So in this context, some of these satellite missions are part of this ESA HERNET third-party missions, which allows and grants access to European users or makes it easier for these European users to make use of this data. The key objective and the role of EDAP, that data assessment project, is to kind of assess the quality and the suitability of these candidate missions for being considered for this TPM. So we will take advantage of these new satellites or all these new constellations and try to integrate them within this TPM. And here is this list of all the satellites that are candidates that goes from optical missions to SAR, atmospheric, IRS, and RF. For what it concerns satellite missions, we have ESA as the main customer, Telespazio UK as the prime contractor, and from the technical analysis, we have Aresis, our Italian partner, and the Finnish Meteorological Institute. So this is a bit of the flowchart of what we have been doing. That goes from familiarization with the mission to the assessment of what is going to be done with this data, to the collection of the documentation and of all the acquisitions that we will analyze further. Then we, of course, do the work, the actual work. We analyze the documentation, we analyze these images, and we produce these technical notes that after a few iterations they get published in this, within this EDAP webpage. So this is a bit on the documentation of what is done. We basically have to fill these kind of matrices with some qualification that goes from non-assess to ideal. This ideal is more like as it says, is ideal. So it's like it's expected for some of these satellite missions not to be able to fulfill. It's like a upper bound if you want to think about it, but it's still really useful for them because it kind of sets like a very good guideline of what is required for them to have. And another important value of this assessment is that we also have access to some data or some of this documentation that is not publicly available. So this is already quite something. These guidelines are in line with this quality assessment for Earth observation framework, and it can be checked in the EDAP website. So for example, if we go to what it means in these product details, we will be evaluating if in the documentation you can find all the product details related to this satellite, like temporal baseline or coverage, or if the name of the data products are in order and so on. If we go, say, to these flags and metadata, we will be evaluating not only if all the flags that are included in the product metadata are properly explained, but also if there is some flag that could be included. And another thing that is important is that we believe that this kind of assessment has a positive effect for the companies themselves, because we have seen in the case of the particular case of ISI from EDAP, from the original EDAP to the EDAP Plus, that the improvement on the documentation have improved. Well, it was quite significant. So then we move to this analysis of the SAR data. So that is divided in these 3 big blocks: IRF, geometric, and radiometric, and over 3 main sites that are like corner reflectors. We have selected classic corner reflector sites around the world, and rainforest as a mean of having a stable target, and also low backscatter areas such as doldrums. The analysis was done using these tools that I have listed just below. This is a Snap toolbox, RSC SAR quality toolbox that is their own software developed by our partner RSC. ICE2 this is more related to what is going to be done, or is a potential software that we will use for EDAP Plus. And another really interesting thing is this is a SAR calibration toolbox that is this kind of, it's like this RSC SAR quality toolbox, but it will be made in Python, open source, and fully available for the community to use. So far, this is what we have done. In black is all the technical notes that you can find today and you can consult. Down below, there is the link, and we have basically done SAOCOM, a couple of ISI satellites, Capella, and PATH, and all of these in red are the ones that are planned for the future. So within this EDAP Plus that it has started a bit over a year ago, and we are foreseeing increasing all these technical nodes and include this INSAR for first time. Well, then ISI, I don't think it needs a very long presentation. This is the largest available SAR constellation, and is already one of these ESA's third-party missions. And one interesting thing is that this is at the bottom we have what is going to be included for the next technical node. These satellites from X8 to 13, X6 for INSAR, ScanSAR, and this SAR video products, this wheel mode. If you haven't, I will recommend you. I haven't dared to put the animation here because I'm not an ISI commercial, but I recommend you going to their webpage and checking these products. They have what I believe is a dock or a harbor, and they have this kind of video mode where they show how a ship is moving. So it's quite cool if you like synthetic aperture radars. Then SAOCOM, again, doesn't I don't think SAOCOM needs neither full presentation. We are still waiting for the data. That I guess it will be a new version of the processor, I believe. So it's coming hopefully relatively soon. So for the INSAR data assessment, what we have planned to do is in EDAP Plus are these 5 points: this interferometric baseline computed from the orbit, annotated in the products, Doppler centroid, annotated in the products, interferometric coherence from interferogram generated, applying co-registration, and using some other technique. And for quadpole, we'll be comparing HH and BB. That is not of relevant for ISA because I don't believe it has such capability. So for ISA INSAR assessment, we have selected this area in the Atacama Desert between Argentina and Chile, and it's a dry mountainous area where we expect to have or observe high interferometric coherence. So now we have this 5 stack of 4 images for each imaging model, both StreetMap and Spotlight. And yeah, this is super recent data. We just received the last of the images, I believe, a bit over 2 weeks ago, or maybe not even. So we are still like doing some of the processing, and this will explain, I guess, a bit the next slide. That is where I have in red all the interferograms that we haven't been able to properly generate. And I believe there is quite a challenging task or major problem with doing this co-registration. I cannot trace back, or I cannot confidently trace back if it's something related to orbit imprecision, or is it something related to this high spatial resolution combined with relatively coarse DEMs. But it came to my mind just in this last presentation by Irena to use these TandemX DEMs that are a bit higher resolution than the ones that I have been using so far. The good news is that in the pairs that are working, moderate to high coherence are observed, but there is some times in this StreetMap that have some strange artifacts. Here is some example of this StreetMap coherence. We can see this is the range direction, so this explains a bit what we are seeing in this cardinal direction or in this east. That is the Chile part. We have high coherence, but on Argentina part, it's quite low, and this is because there is this mountain that also defines the natural border between these two countries, and in that sense, we can really see this, I guess, shadowing effect here. And finally, just to another example of this of another interferogram, but this time for Spotlight, and this is a salt lake. Some of the areas in this salt lake, I don't think it's really reflected in this image, but they are dominated by water. So that explains why some areas are really low coherence, and while the others maintain some relatively high degree of coherence. So just as an overview, I hope this presentation has been of interest of you for what has been done in this ESA EDAP. And I would like to say that we are really interested in the opinion of the community. So if you have comments after my presentation or during this roundtable, we are really looking forward to hear about them. But to summarize, this is the select or these candidate missions considered for this third-party are being assessed right now by us. And yeah, unfortunately, the INSAR data was very short analysis. We haven't been able to produce all the analysis that we would have liked, but I hope it will be done relatively soon, or this can be improved. And I forgot to mention that there are other really interesting satellite missions and constellations like RISAT and Novasat that are, of course, being considered or that not being considered, but they are planned to be assessed. And that will be all from me.
Thank you, Joel.
Thank you. So we have time for questions. Before we move to the final presentation of the session. So maybe I'll ask a quick question. Maybe you might have mentioned, or I missed it, the data sets that you are receiving from the various agencies or companies that you do the analysis and assessment on, are they freely available with the tools? And
I don't think so, no.
Okay.
No.
But you're distributing EDAP Plus, or EDAP is distributing the tools and all the things that you use for the analysis. Is that right?
Well, I think this SAR quality toolbox by RSIS is private, or like they have a commercial license. So I'm afraid no. And the only thing that is available for the users or the potential interested people is the technical notes.
Okay.
All the SAR data is not available, unfortunately.
Okay. All right. Thank you.
So we move to the next presenter, Yu Morishita from Synspective. The title of the presentation is Synspective, a small X-band SAR satellite, Strix constellation, and its first INSAR results. Please.
Thank you. Good afternoon, everyone. I'm Yu Morishita from Synspective, Japan. Today I'm going to talk about Synspective small X-band SAR satellite, Strix constellation, and its first INSAR results. So Synspective is a Tokyo-based Japanese startup company founded in 2018. At that time, I was a visiting researcher here in the University of Leeds, and I joined Synspective last year. And we have raised about $200 million in 4.5 years since the founding. We have a diverse and talented team of 180 members from 30 countries. And we have received several awards like this, and have been recognized both in Japan and globally as a leading startup in the space industry. So we are developing our own small SAR satellite, and the name is Strix. Strix is an X-band small SAR satellite with PV polarization, and its mass is only about 100 kilograms, less than 1/10 of big SAR satellites. Therefore, we can manufacture and launch many satellites at low cost. And one of the characteristics of Strix is revisit period is only 1 day. So this enables the daily monitoring of the ground surface. And only one satellite with 1 day orbit cannot cover whole Earth surface, but constellation with multiple satellites can cover whole Earth surface with 1 day orbit. So this is a roadmap for the Strix constellation. So we launched our first satellite, STRIX Alpha, in December 2020, and we also launched STRIX Beta and STRIX 1 in 2022. So now we have 3 satellites in space and have been operating them to acquire SAR images. And in the next step, we plan to have 6 satellites around 2024, and this can achieve daily observation anywhere on Earth. And then we aim to construct a constellation with 30 satellites by the end of 2020s, and this can observe anywhere near real time within a few hours or less. So current STRIX satellite has 2 observation modes, strip map and sliding spotlight. Strip map has a wider swath width of 20 km and can get a long image around azimuth direction, and the spatial resolution is about 3 meters. And sliding spotlight can cover smaller 10 by 10 kilometer area, but the spatial resolution is higher, 1 meter. So this is the very first image acquired by the first satellite STRIX Alpha in the area of Tokyo. And if we zoom in around Haneda Airport, around here, the image is like this. So we can see some terminal buildings, airplanes, and other structures. So our business is not only developing and operating SAR satellites and selling the SAR data, but also providing solution services. So there is a huge demand for the SAR data from the NS sector, and we are responding to the demand with our own small SAR satellite data, but it is also important to develop the solution services to fully exploit our own SAR data and to make our SAR data fully contribute to the society for example, infrastructure, energy, and finance market. So we ourselves develop the solution services as well as the satellites using other big data science technologies, and of course our own satellite and other satellite data. So this is one of our unique points. We are both a data provider and solution provider. So this is our current solution lineup. We have land displacement monitoring, flood damage assessment, disaster damage assessment, forest inventory management, and offshore wind assessment. So we will improve these solutions using our STRIX data, and we will also develop some new solutions in the future. So one of the solutions, land displacement monitoring, uses INSAR time series analysis technique, and currently we mainly use Sentinel-1 data in this solution, not STRIX. But however, of course we want to use our STRIX data in this solution in the future. However, as you may know, or as you have seen in the previous presentations, INSAR is not easy for small SAR satellites. So as our first step, we investigated the INSAR capability of STRIX using recent data. So this is data information used for the STRIX INSAR trials. So we used both strip map and sliding spotlight, and we selected the areas that covered multiple land cover types, such as urban areas, mountains, and croplands. So the orbit direction is descending left for strip map and ascending right for sliding spotlight. And the observation dates are around the end of January this year with 1-day interval. And the perpendicular baseline is about 100 meters for strip map and 460 meters for sliding spotlight. So these are significantly smaller than the critical baselines, so we can expect high coherence if there is no other problem. And I used multiple factor of 4 in range, resulting in the pixel spacing of 6 meter for strip map and 2.4 meter for sliding spotlight. Okay, so this is the result of strip map interferogram. And the left one is coherence, and the middle one is differential phases, and the right one is optical image. And as for the differential phases, I applied high-pass filter to remove orbital fringes and atmospheric noises, and to extract the local phase changes. So as we can see, we obtained very sufficient coherence and clear fringes in this interferogram. So we can see we have confirmed the insert capability of streaks. Okay, so around here there are urban areas, and the coherence is quite high as expected. So next, let's see some details. So first, let's zoom in on the Sakurajima volcano around the middle, covered with vegetation. Okay, so around the summit or crater, there is no vegetation, and the coherence is quite high here, as expected. And Sakurajima is a very active volcano and erupts very often, like every day. And we can see some small phase changes around the crater here. And these are probably caused by the DM error because of the topographic changes by the eruptions. And surprisingly, we obtained sufficient coherence even in forest areas around here, and also clear fringes. So generally, expanded data cannot get coherent signals in forest areas because short wavelength radar wave cannot penetrate leaves or branches. But in this case, we obtained sufficient coherence in the forest areas. So this is probably because of the very short temporal interval, 1 day. So this implies that expanded data with very short temporal interval, 1 day or even shorter, might have the potential to get coherent signals even in forests. Okay, so let's move to another area, Aira City. So again, we can see some fringes in the forest areas here, and also we can see some small phase changes here, and this corresponds to the query, which would have had drastic surface changes. So these phase changes are probably caused by the DM error, and we would be able to estimate the current true topography from these phase changes. Okay, so next let's move on to the oil tank area. So as we can see, we can see many phase changes corresponding to each oil tanks, and the amount of phase changes vary for each oil tank. And because the roof of these oil tanks are floating, these phase changes could be caused by the actual height difference in 1 day of the floating roof. Of course, some DM error component would be included. Okay, so next let's move on to the sliding spotlight interferogram. So the AOI is Koshigaya City in Japan, including urban areas and croplands. So as we can see in the coherence image, the coherence is quite high over the image, and we obtained sufficient coherence even in cropland area because of the very short 1 day temporal interval. Okay, so next let's focus on the shopping mall area around the middle. Okay, so in this interferogram we can see some phase changes around the buildings or bridges and train lines. And these phase changes are caused by the DM error, or in other words, the height difference between the scattering point and the DM surface. And also, we can see some small phase changes around here, corresponding to the 10-meter scale residential houses here. Okay, so I checked the rough height of the structures here, and I found that the DM error estimated from these phase differences are roughly consistent with the height of the structures. So, for example, this building, the roof of this building has 10-meter height, and this yellow color corresponds to the 10-meter DM error. And this bridge has 6-meter height above the ground, and this purple color is roughly consistent with the 6-meter DM error. So these phase changes, phase differences can be quantitatively explained by the structure of the height of the structure. Yes. Okay, so if we compare the Strix-1 interferogram with Sentinel-1 interferogram, we can clearly see the difference in the spatial resolution. Because the pixel spacing, azimuth pixel spacing of Sentinel-1 is 14 meter, this is the highest achievable spatial resolution of the Sentinel-1 interferogram. So as we can see, Sentinel-1 interferogram cannot distinguish small structures, so this is not suitable for small-scale infrastructure monitoring. But on the other hand, Strix-1 interferogram has much higher spatial resolution and also temporal resolution one day. So this means Strix-1 has much higher potential to detect the small-scale and rapid deformation. So Strix one-day interferograms would be helpful for example, daily monitoring of the underground works. Okay, so this is a summary of my presentation. Synspective has developed and operated small expansor satellites, Strix, since 2018. And 3 satellites have been launched so far, and 30 satellites will be launched by the end of 2020s. And Strix INSAR capability was demonstrated in this presentation, and one-day interferograms showed sufficient coherence even in forest, and fine differential phases with high resolution were successfully obtained. So honestly speaking, current INSAR capability of Strix is very limited because of the undesirable orbit situation. But in the near future, next satellite, we will be able to control the orbit much better, and we will get much higher INSAR capability of Strix. And the next step would be the experiment of INSAR time series analysis using one-day interval consecutive images of Strix. So yeah, thank you for your attention. Thank you very much.
So thank you very much, Yu. We have time for questions. Please.
Thank you for your presentation. I would like to ask, in the beginning, you have shown a graph with 1 day of revisit time and then a few hours. I suppose this is revisit, not recurrence time, I mean, capable of having interferometry?
Yes, but yeah, I cannot change. No, yeah, each satellite have 1 day revisit, and actually we haven't decided how deploy multiple satellites, but this is one option or one candidate. So we have 6 orbital planes, and in each orbital plane, we may have 5 satellites. So in that case, the revisit is less than 1 day. 1 day divided by 5. So yeah, hopefully we can do.
Yes, but a revisit or recurrence. I mean, should they be able to produce interferometry?
Yeah. If we achieve this constellation, we can achieve the interferogram with 5 hours interval, maybe. Yeah.
Okay, so you are planning to deploy towards this?
Yeah, we haven't decided yet, but yeah, this is just one option, one candidate.
Okay. I think most of us here will be interested to have something like this. That's why I'm asking. Thank you.
Yeah, I would have maybe. I think please.
Okay, thank you. I just have maybe one question. Maybe it's not really correlated to this talk, but so what I understood is this constellation is you will have something like 30 satellites, and it will be operate CAPSA separately, independent.
Sorry.
And so CAPSA, that's 30 satellite will be operate CAPSA separately or independent, or maybe is there any figure to do multi-status?
Yeah, actually we haven't determined how to operate or how to deploy it. So yeah, it's difficult to answer in the current situation.
Okay, thank you.
Ramon?
Yeah, thank you. Maybe a very short question. The duty cycle, how much time can you operate per orbit?
A duty, I think I cannot say the detail because it's a kind of confidential, but it's actually current observational resources not much. So yeah, it's much less than, for example, Sentinel-1 or something. Yeah.
So like a couple of minutes per orbit or something?
Yeah, I think so. That kind of level. Yeah.
Thank you.
Yeah, and I would have one question. So, have you defined an orbital tube you are working, or you are going to use approaches as ISI has been doing with larger baselines?
Yeah, orbital tube. So it's not decided, of course, but we are aiming to achieve 500-meter orbital tube, but we don't know when we can achieve it, but it's the objective.
Okay. Yeah, thanks. So if no more questions, so we can move directly to the roundtable, which is going to include also the missions 1 today in the morning. Bjorn, do you want to join us? Oh.
I don't think these are the seat questions.
Please stay around if you want to the roundtable discussion.
Yes. And so, by the way, there is a typo on the program. We don't finish at 4:50 as it's written on the program because there's like 20 minutes shift, so you don't have to stay too late.
Or it will be very short.
So we will probably finish in 30 minutes, but depending on the type of questions that and type of discussions that we have. So the questions that are currently displayed are not the ones that we are going to discuss. As you can see, this is the mission session, not the thematic session. You didn't get it?
The PowerPoint. So where did you send it? Or
So the seed questions will be up in a minute. And so just as a reminder, as a summary, so we had 4 talks this morning in the Mission 1 session and 5 talks in the afternoon. I think the first session this morning was more focused on 3D displacements. There were several talks on the future missions, whereas the afternoon we saw several talks focused on commercial SAR. And so the seed questions are essentially, we have 5 seed questions. The first question is focused on the sort of advanced measurements, such as 3D deformation. So several talks highlighted the need for more advanced measurements, such as 3D displacement retrieval or atmospheric correction or differencing DEMs, things like that, with possible solutions as well. And so the question is, are future missions on track to provide these measurements? So the way things have been highlighted and planned and showed in these talks are adequate, are sufficient in your opinion to address these advanced measurements? And if this is too broad, you can think of your favorite advanced measurement, such as 3D displacements, for example. Is the multi-screen technique or the inclined orbit adequate, or there is more? And by the way, you can also think about the other missions that were shown, I think it was on Tuesday, such as Harmony or Roselle. You can put that in the mix if that helps. There is Ramon.
Do you want to go through this order, or can I also come up with something?
Any order, Ramon. Or any new things as well, so you can just go beyond what we.
Yeah, well, I have to say I was very impressed by the presentation from Yu Xiao on the Chinese progress, and also about his comment about potentially opening data archives there, that this is a subject that is under discussion apparently. And since I think at this week, ESA is also having a Dragon meeting in China as we speak, so there are already relationships between ESA and the Chinese partners. So one recommendation that I would like to give to ESA is to ramp up this collaboration such that also the European scientists can start using Chinese data. Right? I think the data are there. There's an opening. There's geopolitical concerns, obviously, probably, but I would like to give it up to ESA to pick this up.
So they should include Chinese missions as part of the third-party missions, is that?
Right, yeah, so there is I'm very curious about the geosynchronous mission, which is apparently just launched. So we've been, we wanted to launch a geosynchronous mission in Europe already for a very long time. And many proposals failed, so we can learn a lot from them. So a collaboration here would be really great.
Yeah, thanks, Ramon. I just want to comment a little bit. So first of all, sure to bring the words to the relative personnels. And so, as I just mentioned on the stage, so for me as a scholar from university, I don't have a say really in this, but I have been talking to these people. And so from our side, so first of all, we're really benefiting a lot from the past collaboration with ESA. So this is the 5th round of the Dragon Symposium now happening this week in China, as I understand. And so in the past, like 4 rounds, it's almost 20 years, we are really the party who are benefiting and learning from ESA. And we're definitely always keeping an open mind, and we are keeping like a positive attitude towards how we can do this. And so as I just mentioned, we're still trying to figure out a way to do this, so it's really having nothing to do with the other things. It's just a matter of we now need to plan for how things are going. So it's a little bit different. I mean, here I hear a lot of mission, like for the NISAR or like for the ROSL, you have all this very nice plan in the beginning. But on our side, I feel like, so we just launch a satellite and then we decide what we're going to do with it. Yeah, and so now is a point where trying to figure out how we are going to do all these collaborations, distributing data, and also the processing tools, etc. And yeah, so I mean, if we can find a way to work this out, I will be very glad. And I will also myself push this forward, see what we can do.
I think the biggest advantage is that already the connections are made at a high level, right? Between, I think, the Ministry of Science and Technology in China and ESA. So the lines are there, the lines are open, basically.
Regards to question 4, about the observation plan of ESA, maybe there is a gap that is currently still open. The space agencies do not cover the possibility to do INSAR for short temporal baselines across disasters, like for volcanoes, earthquakes, landslides. There is something that is missing. We would like to have INSAR with less than 1 day. I think there is a problem. These new missions, these new expand missions, commercial missions, they manage now to do INSAR with Capella, ISI, CorusSAR, and maybe there is a partnership in order to trigger acquisitions from a scientific alert and ask these companies to do the acquisitions and feel that Sentinel or Roselle or these future missions will not fill because their revisit time is more than 3 or 6 days. I'm not sure I made myself understood.
That's exactly
Sorry.
answers one of the question. Yeah, so fill the gap with fast revisit. Yeah, although I have to say somebody this morning, I think, was talking about putting Roselle and Sentinel-1 off of phase in a way that you get 3-day revisit.
1 day.
Oh, you want 1 day. All right, okay.
Just to complement, there are many processes that we suspect are happening at very short time scales, especially for volcanoes and landslides and also earthquakes, rapid post-seismic deformation. And these things, we can't really observe them with the existing and even planned missions of ESA, I think.
Yeah, no, it's a fair point for sure. Piyush?
This is somehow related to point 4 and filling the gap, but probably more maybe asking ESA to work with these providers to help them acquire imagery that is consistent in geometry with global missions like Sentinel-1 and NISAR. Like from an end-user analytics perspective, at least our experience has been that even if you get images from small-sat providers, they're often in a different geometry, and you have to break your whole analytics chain to sort of seamlessly integrate them. Yeah. Since they are so flexible in tasking and controlling their incidence angles and so on, it would really help if all these small-sat providers acquire over areas in sort of geometries compatible with what Sentinel-1 is acquiring or NISAR is acquiring, so that they can sort of seamlessly work with those data sets.
Yeah, it's for sure useful, but my understanding is that they're trying to do that. I think Capella is making an effort.
Yeah, so my question is related to the emergency. Do you mean like to acquire new acquisitions just for imaging, or to start a kind of time series or interferometry?
Or when if you have a task capability to say compatible with NISAR or Sentinel, rather than having the user pick incidence angles, because then the imagery is going to seamlessly fit into whatever they already have into these large archives, and it'll be easy for the end users to work with those.
Yeah, so, okay, I think I am talking about not new space, but at least Capella has an API where you could, I mean, if you have like a budget or if you are a customer, you can use the API automatically.
So it's not really a recommendation for ESA to change anything. So you keep ESA the way it is, even the revisit, just take advantage of the other. Okay. Yeah, better integration.
And maybe also coordination, right? Because if we have many customers tasking over the same site, we have a lot of, yeah.
Yeah, we have one more comment up there.
Hey, does it work? Okay, perfect. So just a fruit for thought. So I love the idea of mid-inclination orbits, such as Capella is bringing, and obviously it brings the opportunity of, for example, 3D displacement, but how about the opportunities and challenges of gradually changing acquisitions time throughout the day, right? For example, the opportunity that comes to my mind is like mapping the displacement phenomena changing over infrastructure throughout the day, or maybe are there other opportunities or challenges for our insert time series approaches that we currently use that most often assume that the acquisition happens at the same time of the day? Just a fruit for thought.
Yeah, so this is, mid-inclination orbits, the repeat cycle of mid-inclination orbit is not an integer number of days, so the local time of the acquisition will be like drifting. You will see probably effects related to changes of the temperature during the day. Yeah, so this is something probably new when using mid-inclination orbits. What does the community think about that? Can this be modeled, or is this a problem we should investigate?
Yes, perhaps ESA, like a European Space Agency, will have the role also to attract all the swarms, private swarms, or even others. And in case of emergencies and crises, will be able to contribute for early response. And systematically, those data acquired for this kind of missions to be delivered for civil protection, etc. agencies. This could be a recommendation for ESA.
Yeah, I think we do have at ESA already this international charter in effect. And I guess it's true that once all these constellations, these new space constellations will be completely ready, and we're ready to as well address that gap, then it will be automatically integrated. And of course, already with ISI, I think there are already some very good cooperations ongoing. But of course, we have to take in mind as well that most of these constellations we were talking about from the private sector, they're not, let's say, at a full operational level, let's say. So they're still building up their capability.
Yes, of course it is commercial, but just to, I don't know, have also motivation for the companies to participate in any case, so things like that. But anyway, perhaps there has been some collaboration for a few hours response, but if it may drop to lower, also this could be investigated in the future. I mean. Okay, thank you.
Yeah, as you've seen in one of the talks for the EDAP plus data quality assessment, of course, some of these, we're looking already, let's say, what the data quality of these missions are, let's say, and not just relying on what is publicized on the websites, but really looking, let's say, the data set, so the users are aware what they can expect, let's say, from the data in flight.
Okay, so also if there are some kind of data and stream, because if we are talking about very dense acquisitions, it is a stream. This should also trigger for this kind of services. I mean, if there are civil protection linked with research entities, the availability of this stream will trigger these applications also. Okay, thank you.
This is last note on what you were saying. Of course, all these, let's say, if you look at the Sentinel-1 and also Roselle, these were always considered, let's say, wall-to-wall mapping missions, where high-resolution systems could always, let's say, address the gap, let's say, and be able to, let's say, look further, something to look at, let's say, where it needs high resolution or high revisit, that we currently are able to offer. So this was always the plan, I think, in these Copernicus missions in terms of the observation, Christian. That it's clear that you cannot always do everything, and you can't do, and let's say, high revisit and wall-to-wall coverage and high resolution all at the same time. So it has to be, let's say, that gap has to be filled.
Yes, it should be equilibrium, and now with AI, that probably some of the procedures may be automated. This is more prominent to have stream. It could be more easy to be implemented automatically than in the previous years.
Okay, so I have just about the comments on the multi-statis configurations. So I think this will be related to the question number 2 and number 5. So I think there is a gap in terms of the science and technology to understand what exactly the multi-statis can do. So I think that's my recommend is it's better to do some kind of event combine in kind of multi-statis to understand something related to the challenge which related to science and technology. So my recommend is maybe there should be a mission, airborne mission in multi-statis configuration.
How would you envision that campaign, that airborne configuration? How would you?
So I think that's with GoFly, maybe just something like with very maybe straightforward with something like in base station scenario, and then we do something like 5 or 6 satellite or something. I don't have exactly the number, but I mean the multi-statis is quite a challenge for us now in terms of even with the even with Synspective company, they have something like 30 satellite, but they don't have any idea to do technology for multi-statis configuration. So I think if we do dedicate some kind of very specific campaign in the airborne campaign in forest, or for example, we can learn something about technology, what is challenge inside, and the science, what we can get from that one. And also in terms of signal processing, we learn a lot.
Yeah, so you would use multiple aircraft to sort of acquire data, just like the spaceborne scenario. Is that?
Yeah. I mean, we can start. We moved a little bit more easier by airborne campaign, and then if everything fine, and then we can implement this for a mission later. To make it simple.
Yeah.
Airborne campaign.
Yeah, I think the only bistatic campaign that ESA had that I'm aware of, well, actually there's more than one for sure. No, but the only bistatic system is the meta-sensing, is that correct? Or there's more, maybe? Tomosense, but who was meta-sensing, right? Yeah.
Maybe I can respond,
Oh,
Marco.
yeah, that's right.
Yes. So for meta-sensing, and we have flown a few campaigns for ESA. One is the Tomosense experiment, and then we have flown Badensar in a long-track formation for Harmony. But that's the only bistatic system I'm aware of.
In the past, was also an experiment with between ONERA and DLR.
Oh yeah.
It was also but that was quite some time ago. Yes.
Yeah, that's true.
Yeah. So, but it's not okay. So as Julia mentioned, we have, let's say, a system that has been flying, and data has been collected, and especially for the Tomosense campaign, as you've seen at Polinsar, I think the results were magnificent, but it was not coming for free. There was a lot of post-processing needed, let's say, to make sure that all the synchronization was right and all the data was, let's say, could be processed properly. So this is something that we take for the future as well, let's say. But it's something that for these type of airborne campaigns, multi-static, it's quite tricky to implement. So yeah, but okay, we're learning. So and we're doing it. So it's is also looking good. Yeah. Yes, front, yes.
Yeah, I think there's with all these missions now in space, I think there has been more talk about collaboration between agencies and how missions work together. And I really got sort of excited about the idea of these co-flyers as a way to get that initiated. I think the big platforms still are built with whatever requirements a continent, a country has, but a cheaper co-flyer could be financed easier, could lead to collaboration and could unlock science that we currently can't do. So I really am excited about this idea to collaborate on co-flyers, including with potentially the commercial market. I think also the commercial providers should consider that as a cheap way to get additional data and provide additional information and IP by leveraging a more expensive illuminator and co-fly with them.
Yes, Ramon. Yes.
Thank you. Another completely different recommendation. So what I heard about Sentinel-1 Next Generation and Roselle is, and the consideration that there are going to be both in this 12-day orbit with one satellite. So then we have 2 Sentinel-1 Next Generations, 2 Roselle satellites. That means that we have a repeat of 3 days if we do it equidistantly. But a revisit that would be for mid-latitudes probably more than 4 times in those 3 days. So that means that we are going to have data basically every 16 hours or so with the envisioned mission. And that means, in my opinion, that INSAR meteorology, so using the INSAR signal for atmospheric research and basically also for updating numerical weather models, will become much more interesting because the main limitation until now was always the long time that it would take before we have an acquisition. And now we're really getting into the time frame where it's going to become interesting for meteorologists and atmospheric scientists, and also I think for operational products. So the recommendation to ESA is to seek the collaboration with the atmospheric scientists there and foster maybe studies to investigate this leading up to the launch of the next generation Sentinel-1 and Roselle.
So that's a new application, essentially, more than what is currently done. Yeah, for sure.
Say again?
That's a new application. You envision a new application.
Yes, it is. So, for example, Giovanni Nico gave a presentation on this earlier this week. So the idea is already there, but you know, the temporal sampling was always the main limitation. And I think now we're going to get somewhere, right?
Yeah, that's why the geosynchronous SAR came into play as well, of course, as one of its main objectives now. Yes. Carlos, I think you wanted the floor.
Just a quick comment about the collaboration. I would like to highlight that this September we had the coordination group of SAR and we had a workshop at ISA, so the forum is already there. And there are different working groups on different applications, on different things. So the forum is already there for collaboration. Yeah. And also there is an interest to include the private sector. I mean, in the meeting in September, we had Google Earth and all these companies, so we can also include the operator of satellites, so there's no problem. So the forum is already there.
Yeah, indeed.
Thank you.
Yeah, and this SAR coordination is actually ongoing. I can confirm that there are meetings, online meetings. So they are talking. So it wasn't just a workshop that stayed in September last year. Yeah, you are also involved in the conversation. So thought there was another comment up there.
Maybe it's a question of place.
So I just recall, for example, the talk of Rachel from yesterday from Suzushi. She said that outdated DEMs sometimes yield problems. And recalling this talk, I saw this problem spotting up in some other talks. So maybe a recommendation might be to tackle this, to maybe improve the availability of updated DEMs, at least for environments with fast I don't know. I don't have a recommendation how to go further.
Okay, thank you. I was going to ask, do you have a solution? So, but yeah, thank you. So that has been noted.
Yes. Yeah, I think it also goes a bit, let's say, in line with, let's say, differential DEMs and faster revisit, let's say, DEMs that I think, okay, at least Harmony has got it, let's say, in its one of its mission objectives called the topography change. But okay, you have to wait for future missions. You have to wait. You have to be patient. So that's the thing. It's not coming tomorrow. And of course, it's also not, let's say, you may not have, let's say, full global coverage for these type of things because that's not, let's say, its main objective to provide DEMs. But so the missions, there are new missions that are going to look into this and trying to do this, let's say, and try to provide these type of things. But then especially, say, having one DEM is a nice thing. But if you have be able to difference them and have, let's say, short temporal, let's say, revisit, then of course you can look at changing volcanoes, glaciers, fast changing things, even in urban environments. After, let's say, disaster assessment type of thing. So, and this is something for all the temporal lags, let's say, that you look at, let's say, even between SRTM and the first tandem, let's say, DEM between 2012 and 2000, there was already showing some fantastic things. Of course, if you have these things more often, you could do fantastic things, and everyone can use it. This is doing a difference of a DEM that's quite straightforward, luckily. So. But this is something I think that's the next, also the next step of SAR products that will come out, let's say, in the future as well, which will have a gigantic, let's say, footprint. I think on not only on the INSAR community, but far beyond, of course. Yeah. Okay. Yes, in the back.
Hi. Concerning all linking to the China space program, I think it is very interesting the idea of geosar sensor, which of course is not able to cover the whole Earth surface, but can offer very high visit time and therefore also in terms of meteorological application or deformation, soil moisture. It is a very attractive and very new. So I hope that the data from Lutan 4 will be available also in order to inspire the new studies from ESA side for a new geosar for the first somehow ESA geosar satellite.
Yeah, that reiterates what Ramon was saying earlier. Yeah.
So maybe to fill in on this, also Ramon knows very well. We have of course been studying geosynchronous SAR in ESA context for quite some time, and that led even to phase 0 study a couple of years ago in the context of Earth Explorer 10. Okay, we now have a call open for Earth Explorer 12. We may have another proposal, we don't know, but have to be patient. But it's not something that has been on the table and probably will stay on the table, and hopefully it will also allow, let's say, some additional studies that go in the context of looking at, let's say, INSAR meteorology. As someone knows, we've been doing this in the past with MetaWave and also with STEAM, the STEAM study. So these type of things there, and they're still strictly needed to continue, let's say, to continue, let's say, the effort on trying to better understand how to use this type of data. Okay. I think we are.
Yeah, so I don't know if we covered everything or.
Yeah, I had one last, based on the discussion they had in the missions one, we had this, it was very open, I think this point 5, and I think you hinted on this already, let's say a bit, on the fully reconfigurable SAR system constellations, also in Marco's presentation, saying, okay, fine, if you have relatively, let's say, relatively small passive flyers that will be able, let's say, to be reconfigured, so you can, if you have 3 flying the same place, roughly, let's say, you would be able to reconfigure them to do maybe single pass INSAR, if you have more even single pass tomography, or you would be able to extend the swath by just pointing them, as you said, 3 times you have 80 kilometers, if you have 3 times, you get roughly, let's say, 250 kilometers, then you would be able to cover the entire swath, let's say, of the master satellite. And this type of thing, of course, is creative. They're already looking, let's say, at existing programs, or let's say, satellites that are already out there. But maybe one thing was there, let's say, maybe we should just think a little bit out of the box again and think and rethink again this type of interferometric cartwheel concepts that were studied early 2000s, and try to go back to this type of thing with our current knowledge on tomographic processing, on single pass INSAR, and what type of application would benefit most this type of mission concepts. So that was something that I think, but I don't think anyone disagrees with that point. So maybe we should bring that forward as well.
Yeah, and the Polinsar workshop, and you were there too, Bjorn. I think somebody brought up that it's worth revisiting the interferometric cartwheel concept for what we're trying to do.
Okay, I think we can maybe call it a day for this one. And
sounds good.
And then can give you. I think there's a coffee break, and I think the poster session. I think with probably some coffee and maybe some other drinks. Okay, thank you all.
Thank you very much. Bye. Great. So I took some notes, and I can send it to you.